It's a wide open.
It's wide open. We all set? Will the commission come to order, please? Today, the Commission will focus on the events leading to the decision to launch the Challenger. The Commission has already reviewed a good deal of information about the seals and the O-rings on the solid rocket boosters. It should be noted, however, that it is not yet clear that the joint area was the originating problem. Therefore, it is important that all potential causes of the accident, including the external tank, be actively pursued. In our sessions today and tomorrow, we want to present in a thoughtful and orderly manner the facts relating to the decision to launch the Challenger. Because of its importance, I will ask witnesses to identify the time and place of any event that they are addressing and the names and positions of persons who participated. The Commission wants to be fair in the presentation of the facts. Because the subject matter may involve possible human error as distinguished from equipment failure, the Commission will attempt to give a right of reply as soon as possible to any person who believes he has been unfairly criticized or whose actions may have been inaccurately portrayed. During the last 2 weeks, the Commission has encouraged NASA to disclose a large number of facts and documents relating to the launch, which has been done. As a result, we believe the public is better able to understand and assess many aspects of the accident. We hope that this process will continue until all the facts are fully known and as much as possible fully understood. While the Commission has the responsibility under its mandate from the President to investigate the accident and report its findings, the media plays a key role in the process by keeping the public informed. We believe it has performed this role well and with a high sense of responsibility. If the Commission effectively performs its duties and the media performs its role of accurately reporting the facts as they develop, the public will be well served. Witnesses who appear today will be able to comment or to clarify their testimony as long as the substance, comment on or clarify their testimony as long as the substance is not altered. Of course, any additional evidence or additional material that might assist the Commission in the performance of its duties and responsibilities will be welcome. The first witnesses this morning will be Allan McDonald. Following Mr. McDonald and at the request of Morton Thiokol, the Commission will next hear Jerry Mason, who is Executive Vice President of Thiokol. First, I would like to call upon our Executive Director, Dr. Keel, who will make a few comments before we hear Mr. McDonald.
Mr. Chairman, for the benefit of the Commission, we have put together a chronology of events relating to the period when the first temperature concerns were raised with respect to the Challenger, indicating the activities and also the participants as the Commission understands them based on testimony and documentation provided to the Commission. This chronology has been provided to all the witnesses, Mr. Chairman, so that they'll have an opportunity to understand our reconstruction of those events and to clarify them, and also to, as appropriate, to identify the nature of the discussions at each of these meetings and activities, starting approximately from the scrub of the originally planned launch of Challenger for January 27th at 9:38 a.m., ranging up to the launch of the Challenger on January 28th at 11:38 a.m.
There are corrections that have to be made on this document. We'll make them as we go along. It's as accurate as we can make it at the present time. Now I'd like to call on Mr. McDonald, please. Yes. Mr. McDonald, I think if you take the middle chair, it might be the best. I think to be consistent, let's swear all the witnesses in again. Some have been sworn and some have not, so let's swear them all again, please.
Do you swear the testimony you give before this commission will be the truth, the whole truth, and nothing but the truth, shall be done?
I do.
Mr. McDonald, you're now employed by Port Thiokol, Inc.?
That's correct.
And how long have you been employed by them?
I've been with Martin Thiokol for a little over 26 years.
And you're an engineer?
Yes, I have a bachelor's degree in chemical engineering from Montana State University and a master's degree in engineering administration from the University of Utah.
And can you give us some history of your employment with Thiokol?
I'm currently the director of the Space Shuttle Solid Rocket Motor Project. My responsibilities are for technical cost and schedule performance of the steel case motors that are flown out of Kennedy, and also the development qualification of the film long case solid rocket motor to be flown out of Vandenberg Air Force Base. I've had this position for a little less than 2 years. I started as director in March of 1984 of the Shuttle SRM project. Prior to that, I was the manager of the project engineering division at Martin Thiokol, which I had technical responsibility from a project engineering standpoint for all of the programs in the plant, with the exception of the Space Shuttle. That included the Peacekeeper, the MX Stage 1, Trident 1 C4 production, Trident 2 development, the HARM, Mark 104 Standard Missile, PAM-D2, the Improved Performance Space Motor 2, finished a contract on qualification of the Long Life Motor for SRAM. I had all of the independent research and development, advanced technology programs with the Rocket Propulsion Laboratory, and also some work on airbag, air cushion restraint systems. I had that job, I guess, for about 3-4 years prior to coming into the shuttle program, and prior to that I was the manager of the propellant development department for a few years, and prior to that I was the manager of the project engineering group for advanced development and development projects. I started with Thiokol in '59 after graduating from Montana State University, and my first job was involved in designing the external insulation for the Stage 1 of the Minuteman. I did that design, and I was then chosen as a group leader for flight test of the Minuteman, and was participated in the flight test about the first 20 flights of the Minuteman out of the Cape. Subsequent to that, I spent considerable time working as a chief engineer on development of some controllable solid rocket motor concepts for several years, and worked on a lot of advanced development programs before I came involved in the Trident program in the early 70s.
So for the last 3 or 4 years, where have you spent your time?
The last couple of years, of course, I've spent my time as director of the Solid Rocket Motor Project, which involves a considerable amount of coordination relative to production of the shuttle solid rocket motors, assessment of the flight readiness reviews for the Space Shuttle solid rocket motors. I am the chairman of the Senior Material Review Board for the SRM. That Senior Material Review Board has to review all of the discrepancies on any of the hardware that's considered a criticality 1, or any that's outside the experience base of our previous experience. As chairman of that board, there's members from our quality group, our engineering group, NASA Marshall representatives, but I have to sign every one of those that they're ready for flight. I'm also a co-chairman of the Problem Review Board with Marshall Space Flight Center relative to any problems that are identified from returned hardware that come back to the Cape, and what actions are taken to understand those problems and provide proper fixes for those and prevent them from occurring. My activities in the past year, to a large extent, have been involved with design certification of the film along case solid rocket motor. I'm also the co-chairman of the design certification team represented by Thiokol and Marshall at the SRM level for that, and that has taken a considerable amount of my time this past summer in a series of reviews for certifying the graphite composite case for Van and Rip.
Now, how much time did you spend in the performance of those duties at Kennedy Space Center?
Well, I have been alternating with my supervisor, the Vice President of Space Booster Programs, Mr. Joe Kilminster, on the...
Mr. Who?
Joe Kilminster.
And what is his title?
He's the Vice President of the Space Booster Programs. And he and I have been alternating going to the Cape, supporting the launches of the SRMs.
Is he your immediate supervisor?
He's my immediate supervisor, yes.
And you alternated going to the Cape?
Yes.
Now, how did that work?
That works out fairly well. We both, of course, have a fairly heavy demand on our time with all the reviews in the shuttle process, primarily with the trips to Huntsville and the Marshall Space Flight Center. I attended, of course, the STS-51L. He was at the prior flight. And our charter is to attend the L-1 meeting.
F-51L is the Challenger launch.
That's correct.
And you were there at that time. Was he, Mr. Kilminster, there the previous launch?
He was at the previous launch, yes.
What about the one before that?
One before that I was at. And he was the one, I think, before that. We've been fairly well alternating.
Okay. What were your responsibilities when you were there at the Cape at the time of the launch?
Well, at the time of the launch, I was in the firing room 2, Launch Control Center. There's seats there that for the monitors of many of the functions on the solid rocket boosters, as well as the TV monitor. The Marshall Space Flight Center has a group at their console that involves the primary contractors for all of the subsystems. The SRB has one monitor, and they have people from USVI who provide part of the hardware. We also have a monitor from the our support to the Space Shuttle processing contractor that is right next to that monitor, and Mr. Carter Kennedy, our Vice President of our space operations at the Cape, was at that monitor. It's right next to the Marshall monitor, and I was sitting with him at the time of the launch.
I wasn't speaking so much about the Challenger launch as I was generally speaking. Generally speaking, when you or Mr. Kilminster are at Kennedy, you speak for the company, is that it?
Yes. Generally, the process is before a launch, there's an L-1 meeting the day before the launch, at which time all of the problems that were still open prior to the L-1 are reviewed with Jess Moore and his board, and assured that they're all closed out and we're ready for the launch. Subsequent to that meeting, there's a poll that is taken. He takes an oral poll of everyone that's involved in the launch, including as well as the propulsion systems, but the payload and everyone else. And every contractor that is involved in that has to answer to the poll as whether they're ready to go and launch. I attended that meeting. As you know, the L-1 meeting was conducted, I believe, on Saturday or something.
Yes, I'd like to, if you don't mind, come to that in chronologically in just a moment. But so at those meetings, when you were there, you spoke for Thiokol.
Yes, I spoke for Thiokol.
And how long had you been there prior to the launch of the Challenger, physically located at Kennedy?
I was at Marshall Space Flight Center earlier in the week on some negotiations for our subsequent contract, and had went down to Kennedy on the, I believe it was the Thursday before the launch.
Could you give some explanation of the relationship between yourself and Marshall before you went to Kennedy?
I'm not sure what you mean by relationship.
Well, what function was Marshall performing at that time, and what were you doing in representing Thiokol?
Well, Marshall has overall responsibility for all of the propulsion subsystems on the shuttle, and we are part of the SRB team. I work directly with Larry Ware, who is the project manager for Marshall on the solid rocket motor, and he works for Larry Malloy, who is the project manager on the SRB, which includes the solid rocket motor and the aft skirt TVA system and the parachute recovery system makes up the whole SRB. And I always attend, or Joe Kilminster attends, the launches with Mr. Malloy, and he has the representatives also from the other subcontractors for USBI. In case there's any questions that come up that we can either resolve there or get resolution to prior to the launch.
Just for the record, where's Marshall located?
Marshall's located in Huntsville, Alabama.
And when did you leave Huntsville, Alabama to go to Cape Kennedy on this occasion?
Well, I think it was Wednesday or Thursday afternoon before the launch.
Did you go by yourself or with someone?
No, I went by myself.
Now, I want to give you an opportunity to give a full description of the events the day before and the 27th and the day of the launch. Before I do that, I understand that you made some notes after the accident which put on papers some of your recollections of the events that preceded the accident. Is that correct?
That is correct.
And you have those notes now?
Yes, I have those notes.
I would like to explain to you that you're at liberty to refer to those notes in any way you want to. And now, beginning with the first recollection you have of the weather problem and how it came to your attention, give us a full account of the events of that day and the following days, 27th and 28th. We'll try not to interrupt you except possibly for clarification. I want you to feel free to tell everything you recall about it, and then after that we may ask some questions about to try to amplify any answers that you may give.
Well, I first become aware of the concern of the low temperatures that were projected for the Cape. It was late in the afternoon on the 27th. I was at Carver Kennedy's house. He's the vice president of our, as I mentioned, Space Operations Center at the Cape, supports the stacking of the SRMs. And I had a call from Bob Ebling. He is the manager of our ignition system and final assembly, works for me, program manager at Thrakal in Utah. And he called me and said that they had just received some word earlier that the weatherman was projecting temperatures as low as 18 degrees Fahrenheit sometime in the early morning hours of the 28th, and that they had some meetings with some of the engineering people, had some concerns about the O-rings getting to those kinds of temperatures. And he wanted to make me aware of that, and also wanted to get some more updated and better information on what the actual temperature history was going to be predicted, so that they could make some calculations on what they expected the real temperature the O-rings may see.
He was calling from Utah?
He was calling from Utah. I told him that I would get that temperature data for him and call him back. Carver Kennedy then, when I hung up, called the Launch Operations Center to get the predicted temperatures from Pad B, as well as what the temperature history had been during the day up until that time.
And Pad B was the area where the launch was going to
Pad B was the pad that the Challenger was to fly off of, and this was the first time that it would fly off of that pad. He obtained those temperatures from the Launch Operations Center, and they basically said that they felt it was going to get near freezing or freezing before midnight. Could get as low as 22 degrees as a minimum in the early morning hours, probably around 6 o'clock. And that they were predicting a temperature of about 26 degrees at the intended launch time, about 9:38 the next morning. I took that data and called back to the plant, sent it to Bob Ebling, and relayed that to him and told him he ought to use this temperature data for his predictions, and that I thought this was very serious, and make sure that he had the vice president of engineering involved in this and all of his people, that I wanted them to put together some calculations and a presentation material.
Who was the vice president of operations?
Mr. Bob Lund is our vice president of engineering at our Morton Thrakal facility in Utah. So make sure that he was involved in this, and that this decision should be an engineering decision, not a program management decision. And I told him that I would like him to make sure they prepared some charts and were in a position to recommend a launch temperature. Just don't recommend a launch, but recommend a launch temperature, and have the rationale for supporting that launch temperature. I then hung up and I called Mr. Malloy. He was staying at the Holiday Inn in Merritt Island, and they couldn't reach him. So I called Cecil Houston. Cecil Houston is the resident manager for the Marshall Space Flight Center office at KSC, and told him about our concerns with the low temperatures and the potential problem with the O-rings. And he said that he would set up a teleconference. He had a 4-wire system next to his office. His office is right across from the VAB in the Trailer Complex C over there. And he would set up a 4-wire teleconference involving the engineering people at the Marshall Space Flight Center at Huntsville, our people back at Thiokol in Utah, and that I should come down to his office and participate at Kennedy from there. And that he would get back with me and let me know when that time would be. I waited for a short period of time. I don't know exactly how long. It wasn't very long. He called back, told me that he had contacted the parties and it was all set up for 8:15 p.m. Eastern Time for that teleconference. I relayed that message on back to the plant, told them that we have to have charts at that time faxed out to Kennedy as well as Marshall that we could discuss for that teleconference.
Could you explain what charts mean?
Well, they're charts, any data that we had for showing why we had concerns on the O-rings of low temperatures, what our history has been, what any calculations we might be able to make relative to their performance, supporting it, rationale for what an acceptable temperature, what might not be an acceptable temperature, and to review that. And these would all be on charts that we would send by a fax machine so people could read those and we could discuss those as the rationale for either recommending a launch or not. I arrived at the Kennedy Space Center at about 8:15, and when I arrived there at the Kennedy Space Center, the other people that already had arrived were Larry Malloy was there. He is the manager of the project manager for the SRB for Marshall. Stan Reinhardt was there, and he is the manager of the shuttle project office. He's Larry Malloy's boss. Cecil Houston was there, the resident manager for Marshall, and Jack Buchanan was there. He happens to be our manager, Morton Thiokol's manager of our Launch Support Services office at Kennedy. The telecon hadn't started yet. It came on the network shortly after I got there, but was told to hold on because the charts had not been received either at Marshall or Kennedy at that time. And we waited, I guess, for probably another half hour before those charts finally came through and we could reproduce them. In fact, they hadn't all even been received yet. There were some conclusions, recommendations charts didn't come for about a half hour even later than that. But
was it essentially a telephone conference, or was there actually a network with pictures?
It was a telephone conference, just telephone. You could hear the voices from the other two places as well as your own. However, the way those teleconferences work, there's buttons that you can push, and will mute out you speaking. If someone else is speaking, you can usually hear it better when you don't have your own mics open. So there's a lot of conversations, I'm sure, at all the facilities at one time, which you can't hear, but I'll relay on what I had heard on the conference as best I can. The teleconference started, I guess, close to 9 o'clock, and even though all the charts weren't there, we were told to begin, and that Morton Thiokol should take the lead and go through the charts that they had sent to both centers. The charts were presented by the engineering people from Thiokol. In fact, by the people that had made those particular charts. Some of them were typed, some were handwritten. And they discussed their concerns with the low temperatures relative to the possible effects on the O-rings, primarily the timing function to seal the O-rings. They presented history of some of the data that we had accumulated both in static tests and as flight tests relative to temperatures and performance of the O-rings. They reviewed the history of all of our erosion with any O-rings in the field joints, any blow-by the primary O-ring with soot or products of combustion or decomposition that we had noted, and the performance of the secondary O-rings. And there was an exchange amongst the technical people on that date as what it meant and discussions. But the real exchange never really came until the conclusions and recommendations came in. At that point in time, our Vice President, Mr. Bob Lund, presented those charts. And he presented the charts on the conclusions and recommendations, and the bottom line was that the engineering people would not recommend the launch below 53 degrees Fahrenheit. The basis for that recommendation was primarily our concern with a launch that had occurred about a year earlier, in January of '85. I believe it was 51C, was our motor number SRM-15. And that particular motor had a couple of field joints that not only had some erosion, but they had some fairly severe blow-by. The primary seals, fairly heavy soot over a fairly large arc, very deep and black. And even though we could see no measurable erosion on the secondary O-ring, there was a heat effect. And by that, the sheen was gone off of the O-ring seal. Couldn't measure anything, but the sheen was gone. And because of that, we were concerned of launching beyond our experience base below that temperature. Well, that temperature brought a lot of strong comments and reaction from several of the NASA officials. I believe it was Mr. Malloy made some comments about when we'll ever fly if we have to live to that sometime in the future. And also commented that we are trying to establish new launch commit criteria. We can't do that. You don't do that the night before a launch. That's a predetermined set of constraints, and we can't do that. And other comments were made about whether we could ever fly out of Vandenberg and 24 flights a year, because it wasn't uncommon to have 53 degrees in the early morning hours where a lot of the launches occur. One of the comments that came, and this was by voice recognition, I believe it was from Mr. Hardy at Marshall Space Flight Center, was that he was appalled at that recommendation. However, he also said that he certainly wouldn't fly without Thiokol's concurrence.
He would not fly?
He would not fly without Thiokol's concurrence, even though he was appalled at that recommendation. I believe it was Stan Reinhardt's made a comment that he was under the impression that the solid rocket motors were qualified from 40 to 90 degrees, and that 53-degree recommendation certainly was inconsistent with that. Someplace in the conversation about the impact of 53 degrees, I believe Cecil Houston at some time commented that, it wouldn't be till about Thursday that we would have morning temperatures probably in the 50s. So he didn't seem to be as alarmed about when, we could get to that temperature. There were several challenges relative to what was felt, how conclusive the effective temperature was on this whole problem of O-ring erosion or soot blow-by. And the challenge came from looking at the total data, because even though we were as concerned about this flight, which was the coldest ever at that time from Florida, a year earlier, there was that flight back in the late fall of '85, I think it was probably October, 61A, was our SRM-22 set, that had some blow-by the O-rings. No erosion of the primary O-rings. In fact, a couple of them, I believe. And this happened to be a launch that had the highest temperature. So there was some concern that the data was inconclusive. And also that we had some motors that were static tested as low as 36 degrees Fahrenheit, DM4, I believe, and that it showed not only no O-ring erosion, but no blow-by. Well, some of the comments that came back from that, and I believe it was Roger Boisjoly commented that he felt that there was a significant difference in the observation of the actual soot that passed the primary O-ring on the SRM-15 set that was a cold one versus the one that was warm. That there was a much larger arc between the two O-rings that was affected with soot, was much blacker. It penetrated all the way up to the secondary O-ring, and of course we had some heat effect there, and he thought there was a significant difference, and that well could be the difference just due to temperature. I commented at that time about the static test history. I told him I did not feel that that was a valid data for a couple of reasons. One, on the static test motors, we keep the static test motors in a environmental building, essentially, during the build-up, assembly, and checkout of all instrumentation. And that environmental building is kept at 70 to 72 degrees. That building is then rolled back on a track about 6 hours before the static test, so it wasn't exposed very long to the cold temperatures. And secondly, in the static test motors, we went in and actually repaired and filled holes in the putty. These holes are formed by the assembly of the rocket motor. As you form the tang clevis, there's air trapped in there. And that air's got to go someplace. And sometimes that air will go up through the putty. We have seen this, and also when you run the leak check on the two seals, if you get any blow-by during the leak check, it may tend to propagate those. And in the static test motors, some of these were observed, and they went in and filled those inside the motor prior to static test. So I told them I didn't feel that that data was conclusive, and they shouldn't use that for deciding what the O-ring performance was. At that time, there was other discussion on some of the charts that we had that was somewhat inconclusive. We had a chart that had some subscale data where we had run some tests on blow-by with some subscale O-rings. They actually had the full-scale diameter, 280 thousandths, but they were smaller. That was the cross-section of the O-ring with their smaller diameter hardware. And they were cold gas tests, and we were attempting to try to measure what kind of blow-by one might get with the pressurization rates you see in the motor. And we were using argon as the working fluid, and also I think some freon. And we had run tests at around ambient 30 degrees in those and did not see any difference. So there was some conflicting data there. It said it wouldn't make any difference, but that, I want to remind everyone, was a cold test. That time I commented at the time that I felt that lower temperatures were in the direction of badness for both O-rings because it slows down the timing function for both of those. But the effect is much worse for the primary O-ring compared to the secondary O-ring because the leak check forces the primary O-ring in the wrong side of the O-ring groove while it forces the primary O-ring in the proper direction. This fact should be weighed and considered in making an evaluation as to what the recommended temperature should be. I was looking at a chart at that time that we had. In fact, it's a chart that I had made with some help of our engineering people back last summer in a presentation I had made here in Washington to headquarters people in August 19th. There was a chart that showed that there's really three phases or three regions of concern and during the ignition transient relative to the performance of the O-ring. First phase of that is a condition where the O-ring, the primary O-ring is pressurized. It starts as an energizing process and actually has to move from the forward face of the O-ring groove because that's where it's at as a result of leak check. And then it has to move back and seal on the back face. And this process we felt took place in the early part of the ignition transient, someplace before it got to 200 psi. And in cold weather, what's going to affect that is, of course, the grease that's in that area also is very viscous and stiff. The O-ring itself is stiff. We knew that the cold temperature shrank the O-ring some. And from our resiliency tests, which are tests that basically show how the O-ring responds when you have it under some compression and release that load, shows that as it gets cold and stiff, it doesn't want to respond very well. And I looked at it something like a flat tire on the bottom of a, I remember when I used to drive nylon tires when it was cold, I'd get out and there was a flat spot on them. And that O-ring having to move, it either's got to slide or it's got to roll somewhat. It's not a very big dimension it moves in. It's 20, 30 thousandths. But certainly can't be as good as when you don't have that. Also being hard, it then has to extrude into the gap between the two O-ring seals. And the harder it is, I'm sure it's harder to extrude in that gap, which means it may take a higher pressure to do that, which also takes longer time. I felt that based on what we had done in the past, we had concluded that this blow-by phenomena had really occurred in this first part of the pressurization cycle. And I think there was good evidence that it had, because the soot that appeared between the two O-rings was exactly that. It was soot. We analyzed it, but it didn't see any heat effect on the metal at all. In some cases, it discarded the grease, but didn't really burn it. Some of it was a product of the grease. We could not see any real effect on the secondary O-ring, so it couldn't have happened very long. It couldn't have happened under very severe conditions. But at the same time, the temperature effects were concerning, that maybe we're going into another timing regime. However, if we felt that we had a good margin there, then we felt that we do have a good secondary seal during this time. And I think there's been some misconception about the redundancy of the secondary seal. The secondary seal is indeed redundant until the metal parts between the tang and the clevis actually rotate. It's a full redundant seal, and during this time period it is redundant, and that's important. But once those metal parts rotate and you have a problem with resiliency, it may not be. So that's why I was concerned about that area, but if we could convince ourselves that the data said it wouldn't make that much different in that part of the phase, then it would be a reasonable recommendation to say that we would expect much different performance. But shortly thereafter, that Thiokol was asked about their recommendation. I believe, and Joe Kilminster was asked himself what his recommendation would be, since it was engineering that recommended not flying at 53, and he said that he would not go against that recommendation. He couldn't go against it. But based on the controversy relative to how conclusive the effects of temperature actually were on this phenomena, we were asked to reassess and reevaluate that data. And we decided we would do that, and the people at Utah said that, well, they would like to have a caucus for about 5 minutes and go offline.
Could I ask you to stop there just for a moment and go back? We'll come to the caucus in a minute, but go back and explain what was said to convey the decision of no launch. I gather at that point the decision by Thiokol was to recommend against a launch.
That's correct. It was at that point the recommendation was not to launch below 53 degrees.
Who did this talking on that subject? Was it?
That was Bob Lund, the Vice President of Engineering, presented that position. But
were you able to ascertain from that conversation how the engineers as a group stood on that?
Well, the engineers as a group, I can't speak for the group. I was not there, but I did hear the engineers that presented the charts, that they actually presented as part of that supported the 53-degree recommendation. And I felt they're very strong in their conviction as to why they felt uncomfortable to go outside that experience space.
And who were they?
Roger Boisjoly, I think, was one of the strongest ones, and Arnie Thompson, that presented those positions and presented the charts.
And Mr. Lund himself at the time?
Yes, Mr. Lund himself at the time didn't present the detailed technical charts, but he did present the conclusions and recommendations, and that was his recommendation as Vice President of Engineering.
Was anybody on the who's on the telecom from Thiokol's side recommending launch?
At that time, no. There was no one that recommended launch, and I don't recall there was anyone at either Marshall or Thiokol from NASA that didn't agree that cold temperatures went in the wrong direction, didn't help anything. But no one from Thiokol at that time recommended launch.
And what were the comments by NASA officials about that recommendation that you recall?
Well, as I recall, there were some fairly strong comments about being appalled by the recommendation, about trying to institute new launch commit criteria at the last minute, about when we'll ever get this launch off. I thought those were fairly strong comments.
And those were comments, according to your recollection, were made by whom?
Well, the comments relative to the launch commit criteria and when we'll ever get this off was made by Mr. Larry Malloy. The comment about being appalled was George Hardy. He was at Marshall. I think I recognized his voice, but that was by voice recognition.
So it was decided that are there any questions the members of the commission have after that?
Mr. McDonald, I have one question. Before you went off the net, did you ask or make a comment about the secondary O-ring seal seating? That has been
Was I asked to make one?
No, did you make a comment?
I did make a comment, yes I did.
Could you recall that comment, please?
Yes, I think I read it to you, and I'd be glad to do that again. I made the comment that lower temperatures are in the direction of badness for both O-rings because it slows down the timing function. But the effect is much worse for the primary O-ring compared to the secondary O-ring because the leak check forces the primary O-ring into the wrong side of the groove while the secondary O-ring goes in the right direction. And this condition should be evaluated in making the final decision for recommending the lowest acceptable temperature for launch. That was a comment I made.
That confused some people. Some of the witnesses I spoke to thought that was a comment in support of the launch, the fact that the secondary O-ring seal would seat.
Well, that comment is a good news, bad news comment. There is good news and there's bad news. The good news is that the secondary seal is in the right position, but that's not unique to temperature. It's always that way. The bad news is that the primary seal is the one we're depending on for the full ignition transient, and it's going to be a lot worse than it was. But even the secondary, as I mentioned, wouldn't be as good cold as it would be normally.
But by this comment, you were not supporting the launch.
No, not by that comment. I wasn't supporting the launch. I was just saying that's an important consideration, and I felt that if we could run some calculations to show that the temperature did not affect the timing, then that would be supportive of a launch. If it did, it certainly, and that was the concern, that if it pushed that timing out long enough, we had a chart in there that said that if that timing goes beyond that 200 psi regime while you're still eroding the primary O-ring, that for whatever reason, if you ever bypass it at that time, you can't depend on the secondary, and that's what's important.
Thank you.
Because then you never favored launch.
No.
And you made it clear that you were opposed to launch.
Well, I never said I was opposed to the launch. I just made a few comments about why I thought some of the data was not appropriate, like the static tests were saying the O-rings were good to 36 degrees. I made this comment about the lower temperatures affecting both O-rings, but it affects them a little bit differently because one of them, it's a dynamic O-ring. It moves. One of them has a lot more movement and effects on it than the other one does because it has to move across the groove. I made those comments.
But you accepted the recommendation?
I accepted the recommendation, yes. I thought it was an appropriate recommendation.
In other words, you accepted the recommendation of no launch that was made by your company?
That's correct.
Mr. Armstrong?
Would you be surprised if your comments were interpreted by both your own company personnel and Marshall personnel as being supporting of the Marshall position?
Yeah, I would be surprised at that, yes. I think I wouldn't be surprised that that would be evaluated as the effect of that, but I'm surprised that was interpreted as supportive, yeah.
Thank you.
Okay.
You mentioned the 40 to 90 degree qualification limit. Was that referring to ambient air temperatures?
Well, I had a discussion about that later. It was my impression that the motor itself was qualified from 40 to 90 degrees for operating. And we got into a discussion, in fact, during the caucus that was supposed to last for 5 minutes, that lasted for about a half hour on that very subject. I told the people that were there from NASA that I, first of all, didn't agree that the motor was even qualified from 40 to 90 relative to all of its elements and subsystems. I wasn't there in the qualification of the steel case motor, but I just recently went through that process in the film wound case SRM, and that I'm not aware of the testing or analysis of the O-rings were good to those temperatures, and that therefore it's part of the elements, and the way I interpreted the spec is that all of the components and elements that make up the SRM should be qualified at those temperatures. Larry Malloy at that time told me, well, no, the 40 degrees refers to a propellant mean bulk temperature. And the propellant mean bulk temperature was being predicted to be 55 degrees for that launch. And that as long as the propellant mean bulk temperature wasn't below 40 degrees, that you could expose the other parts of the motor to lower temperatures as long as you didn't drop the propellant mean bulk temperature outside of the 40 degrees. I responded, I told him I thought that was absolutely ridiculous because you could expose that motor to very severe cold temperatures, sub-zero temperatures for a fairly long period of time, and you wouldn't change propellant mean bulk temperature at all. There's such a massive amount of propellant insulator there that it takes a long time to do that, and I'm sure that the spec really didn't mean that you could do that. And so my interpretation is certainly different than his.
Was there, in fact, a minimum temperature established by specification or by rotor in some manner that related to the O-rings or the joint?
Well,
at that time,
I wasn't aware of one for the O-rings. I found out later that there was in our specification, it refers to a higher level specification, which is level 2 at Johnson. I think it's 07700 spec. It says that the shuttle vehicle has to be capable of launching in 31 to 99 degrees or something like that, and therefore, since it's a higher level spec, that we should be able to comply with that. But I'm not aware that all of the elements and subsystems were qualified for that.
What do you mean by higher level spec? Could you explain that, please?
That specification comes down from the Johnson Space Center, who is responsible for the overall operation of the vehicle, shuttle vehicle, and what it's capable of operating in the environments, both pre-flight and flight. And that specification for the overall vehicle gets incorporated as part of the lower level specifications that go through level 3, which is Marshall Space Flight Center, to the various elements, and they refer to that. And when they refer to that, the way the system's supposed to work is you're supposed to comply with your own specification plus any higher level specifications that may involve the entire shuttle system. And I was unaware of that, frankly. That criteria was in there. I'm still a little bit puzzled about it because it doesn't have any time limitation on it either. It was 31 degrees for 5 minutes or 40 days.
Now, was there a Thiokol design temperature limit at the time this motor was designed with respect to low temperatures?
I really can't answer that because I wasn't involved in the original design qualification.
Thank you.
We can come to some of these other questions. I'd like to continue the chronology because we were going fine and you stopped about the caucus. Mr. Armstrong has a question, and
then your answer that you just gave. Had Morton Thiokol, to your knowledge, ever informed NASA that the launch commit criteria were inadequate or did not, in fact, cover the kinds of conditions that you were concerned about?
I'm not aware they ever did, not to my knowledge.
And so we're really talking about an event that was within the launch criteria, launch commit criteria, but outside what your experience base was.
Well, I guess I'm not convinced of that either. I didn't learn about the 31 degree thing until sometime afterwards, but we were told to make this evaluation on the basis of launching at 09:38 in the morning where the predicted temperature was 26 degrees Fahrenheit. That was predicted temperature, and that was the decision that's made whether we could launch at that time. So I'm not sure where that came from either.
Dr.
Yeah, just one follow-up to Neil's question. Are you aware of NASA ever asking Thiokol to qualify the SRM or the SRB to 31 degrees?
I'm not aware of it, but again, I wasn't in that part of the program. They may have. I can't say.
If we may now, let's go back. You said that a suggestion was made that have a recess for 5 minutes. Who made that suggestion?
That suggestion was made from someone at Thiokol. I can't recall whether that was Joe. I think it was probably Joe Kilminster, but I'm not sure.
Okay, now what happened? You said that lasted almost a half an hour instead of 5 minutes?
That's correct.
And during that time, what did you do and who were you with?
Well, I was in the conference room at Kennedy with Mr. Reinhardt and Mr. Malloy, Mr. Houston, and Jack Buchanan still, and I gave you my conversation about interpretation of the qualification temperature there. I also commented at that time that I suggested that maybe we consider a late afternoon launch. I didn't feel good about the low temperature launch, because when I had first come down to Kennedy, the original schedule was to launch that in the late afternoon, I think 3:45 or something like that, and based on the weather report I heard, the temperatures would be 48 to 50 degrees in the late afternoon. So I said, why don't we go to a late afternoon launch? And I was told that that was considered, but it was rejected because of some problem either with visibility or weather at one of the transatlantic abort sites. I think it was Dakar or Casablanca, one of those. I really expected the reason it was taking so long for this 5-minute caucus was that we were either trying to find some more information to support our recommendation, or that we were trying to run some kind of calculation to determine how far away from that we could go, because clearly 26 degrees is a long ways from 53. I personally felt we certainly wouldn't go below 40 because I thought my interpretation of qualification was correct, and we wouldn't do that. But that reason it was taking long is the engineers were reassessing all the data they had and finding any more that they may have and trying to quantify more of it. A lot of that data was very qualitative. And finally, the people from FACL in Utah did come back on the line after about a half hour, and I believe it was Joe Kilminster came on the line and said that even though we had some concerns about the lower temperatures, that we would recommend that they proceed with the launch based on the fact that we felt the temperature data that we had was not totally conclusive. And he outlined several concerns still that we had relative to the effective temperature, but also some rationales why we felt it was safe to proceed.
Can you relate what he said?
Well, it was the information basically that ended up finally on the fact statement relative to our concerns of the O-rings being colder and harder, and, but that we also had some data that was inconclusive relative to temperature, and I'm sure it was the warmer temperature launch where we had some blow-by. I didn't see anything that I recognized that was new information, but maybe they had some, and I felt all the engineers were certainly there that had generated the original data and evaluating it, and maybe they had reconsidered or reevaluated the data they had and tried to quantify it, or felt it was probably okay. When he completed that, he was asked, I believe it was by Mr. Hardy, I'm not sure, to put that rationale in writing and to sign it. Make sure to get it down to the Cape, I think by morning, early morning. And I was sitting across the table from Larry Malloy at the time, and I said, well, I felt that I was one that was going to have to sign it because I was at the Cape. I said I wouldn't sign that. I couldn't. It'd have to come from the plant. Joe Kilminster said that, he would draft a letter or a statement and send it down, and he would do it tonight, wouldn't wait until morning, and I was instructed to stay there until that came down, and he would also send it out to Marshall, and it'd be a few minutes before that would come down. He went off line at that time, and I asked Cecil Houston where the fax was, and he told me it was at the other end of the building. I had a conversation with people at FACL just before they went off the line, where they can send that information into Jack Buchanan's office, which is the fax machine right next door to this conference we had, or they can send it into the Marshall office. They had a Pitney Bowes machine or something, and they said, well, we'll send in the same one we send all this other material because they have the right number and all, and that happened to be the Marshall one, which was the other end of the building. So I said, fine, I would wait. Again, took some time for that fax to get there, so all of the parties were in a meeting, were still sitting there, and we started to talk about some things. I told them I didn't feel very good about this recommendation, and that I recognize it's very difficult to quite quantify at which temperature these seals may be acceptable and where they aren't acceptable. You know, based on that data, some of it certainly was inconclusive. There's no doubt in my mind. And that's a difficult thing to quantify, but even though I didn't agree with the 40-degree qualification of the motor, that all elements were qualified to that, it's my understanding that there's a lot of people at both NASA and Thiokol signed up to that through the design certification process, through the critical design reviews. And I was absolutely surprised that NASA would accept any recommendation below 40 degrees Fahrenheit, especially when the predicted temperature is as low as 26 degrees Fahrenheit. So I may be naive about what generates launch commit criteria, but I was under the impression that that was generated based on the qualification of all elements or subsystems of the Space Shuttle, that anything that was outside that qualification was a launch commit criteria, and we never went outside that envelope. And I don't know why NASA would ever launch below 40 degrees Fahrenheit if that's what the SRM was qualified to. In fact, I made the direct statement that if anything happened to this launch, told them I sure wouldn't want to be the person that had to stand in front of a board of inquiry to explain why I launched this outside of the qualification of the solid rocket motor or any shuttle system. When I made that statement, no one commented on that. I was still very upset, so I asked that they reconsider this decision for 3 reasons, not 1, for 3. And I said if I were the launch director, I'd cancel this launch for 3 reasons, not just 1. First one being the concern of the cold O-rings that we just discussed, but there were 2 others. I just left Carver Kennedy's house in Titusville, Florida. And he's responsible not only for stacking of the SRMs, he's responsible for the retrieval operations. And he had been in communication with someone that was at Hangar AF, I believe, that contacts the booster recovery ships at sea. And they had told him that the booster recovery ships were in an absolute survival mode, was how they put it. That they were in seas that were high as 30 feet. There was winds at 50 knots sustained, gusting to 70 knots, pitching the boat as much as 30 degrees. They even felt the rough seas may have damaged some of the retrieval equipment on the back of the ship. They were steering directly into the wind, heading for shore at about 3 knots, and they've been doing that for some time. There's no way that they would be able to support an early morning launch because they wouldn't be in the recovery area. I then reminded everyone in the room that, there's some firsts on this launch. This is the first time that we're going to use the new electronic control system for separating the nozzle extension cone on the SRBs at apogee rather than just before water impact while it's under full main parachute. And then we were going to separate the parachutes at water impact for the very first time on this launch. And that, based on the sea states that I had just heard, that appeared to me that it was going to be nearly impossible to recover that hardware, either the parachutes or the thrusters. And also I felt that they were putting the boosters at some risk as far as recovery was concerned because the ships were steering away. I also said that the third reason for not launching is the formation of ice. I knew the sound suppression system's a water system, and I felt there'd probably be a lot of ice around there, and I'm no expert on all these matters, but I do feel that there may be a chance of that changing the acoustics, may be a problem with debris, may have some effect on the structures. I didn't know, but I didn't think it was prudent to launch under that kind of a condition. I was told that, these weren't really my problems, and I really shouldn't concern myself with these. But I said, all 3 of these together should be more than sufficient to cancel the launch. If the one that we discussed earlier wasn't. The NASA people who were there said that, they would pass these on. They could tell I was disturbed. They would pass those on as concerns, and that they would do it in an advisory capacity. I was then asked by Mr. Malloy where the signed fax was, because some time had transpired since the teleconference had ended, and it still wasn't there. So I said, okay, I'll go check on that. And I went down to the other end of the building to this fax machine, and there was nothing there. It hadn't come out yet, and I really wondered if it was working. It was getting kind of late. So I stayed down there, I guess, for about 10 minutes, and it finally came in. I brought the fax back. It was a single sheet of paper to Jack Buchanan's office, where we reproduced copies for everyone. I walked into, I think it was Cecil Houston's office there, and there was a telecon being conducted, and I believe it was with Arnie Aldrich. And they were in the middle of this telecon, and they were discussing the conditions of the booster recovery ships and the high sea states and the fact that they were in the survival mode. And I recall that Arnie Aldrich asked Larry Malloy if he felt there was any risk to recovering the boosters because of this, and he said no, he didn't think there was any significant risk in recovering the boosters because they had beacons and monitors and they were going to have aircraft in the area also, but that there was a high probability that they would not recover the parachutes or the frustums. And the conclusion was that I guess they'd have to make a decision to launch on the basis that they would have a high probability of not recovering that hardware, but they weren't compromising the recovery of the boosters significantly. And I remember Arnie asking Larry, the value of that hardware, and I think he gave some number close to $1 million, and asked him if he could, afford to lose it and support the schedules of the program. And he said that he had sufficient inventory to do that. But Arnie also told him that in no way have those ships attempt to turn around in those kinds of conditions, and the safety of the ships is important to try to support that launch and turn around too soon. So to tell them to continue on toward shore until it was really safe to turn around. They then briefly discussed the ice issue, about the ice, and there was a concern raised there, and Arnie, I believe it was Arnie, responded that they had discussed that issue earlier in the day. So it was a fairly brief conversation.
Arnie is Mr. Aldrich.
Yes, Mr. Aldrich. They also made it clear that they were acting in advisory capacity only. They weren't making some recommendations or acting in advisory capacity, but wanted them to be aware of this information. I didn't hear anything discussed about the O-ring steel problem. I presume that was done while I was down waiting for that fax, because that was the first concern.
But you're not sure of that?
But I'm not sure. I presumed it was, because I got in the middle of the conversation on the boosters and heard the ice, so I don't know. And finally, the conversation concluded, and the recommendation was to proceed on with the launch. I stayed around a few more minutes and talked to Jack Buchanan for a few minutes, and went back to Carver's house in Titusville, where I stayed, and got in there, I guess, a little before 1 o'clock sometime. And, I guess that's all I can say.
A couple of questions. One, when you first appeared before the commission, I remember you explaining the fact that your company originally had recommended against the launch, and then you testified that after the caucus, they came back and changed their mind, said go ahead with the launch, and you said it was based on inconclusive data. And I remember asking you, how could they have changed their mind based on inconclusive data? Can you explain that?
Well, I can't explain that. That was a comment that was made that the data was inconclusive relative to the effects of the temperature. I prefer you ask those questions to those that made that decision. I don't know. I wasn't there. I wasn't there when all that data was reassessed and evaluated and what the conclusions were drawn.
One other question. Dr. Keel asked at the conclusion of your testimony in executive session whether you felt that you were under pressure or had been under pressure, or the company had been under pressure to reverse its decision. I think your answer was yes. Do you remember that?
Yes, definitely. There's no doubt in my mind. I felt some pressure. I feel that I have a responsible management position in here, and I felt pressure.
Would you explain the reasons for the for feeling pressure?
Well, I've been in many flight readiness reviews, probably as many as anyone in the past year and a half at Thiokol. And I've had to get up and stand before, I think, a very critical audience at Marshall, a very good one, justifying why our hardware was ready to fly. And I have to get up and explain every major defect and why we can fly with that defect. And to the most part, they're very minor, very, very minor. And I've been hassled about how I'm sure that that's okay to fly with. Now, such things as losing vacuum in a carbon cloth-phenolic part in the nozzle, well, the part's basically cured. Now, it doesn't really affect it, but it's a critical process. There's a lot of those critical processes. And I have to address every one of those to great detail. That's why I'm sure that that part has not been compromised. And it's been that way through all the reviews I've ever had. And that's the way it should be. It's not pleasant, but that's the way it should be. And I was surprised here at this particular meeting, the tone of the meeting was just opposite of that. I didn't have to prove I was ready to fly. In fact, I think Bob Crippen made the most accurate statement I ever heard. His conclusion in that meeting was the philosophy seemed to have changed because, you know, he had the same impression I did, that the contractor always had to get up and stand up and prove that his hardware was ready to fly. In this case, we had to prove it wasn't, and that's a big difference. And I felt I was pressured.
And can you explain a little more what source the pressure came from in your mind?
Well, I think the strong statements were made by Mr. Malloy and even some of those people at Marshall that were on there. Mr. Hardy were, I think, fairly strong statements that I took as pressure about when we'll ever fly this thing and launch commit criteria that we can't generate at the last minute, and appalled by our recommendation to fly at temperatures high as 53 degrees, and that, to me, that was pressure to me, and it may not have been interpreted by others, but it was pressure to me.
Any other pressure that you want to refer to at this time or at any time?
No, I just felt that the way the comments were made, as strong as they were made, and the fact that the conditions for justifying this launch were so much different than anything I had been involved with before.
As far as the telefax is concerned, would you normally have signed that telefax, or was the procedure that was followed the normal procedure?
Well, I'm not sure, I guess, what the normal procedure is. I felt that since I was there representing as the senior official at the Cape, then I'm the one that usually is responsible for that. I know at the L-1, when we have a normal launch, there's a poll that's conducted by Jess Moore of all the contractors where they're ready to fly, and I'm the guy there that has to get up and say, yeah, Thiokol's hardware is ready to fly. I felt that's my responsibility. That's why I'm there. I can't recall where we were asked to sign anything like that before. We have a presentation that's given at every flight readiness review that's signed off by the principal parties. Joe Kilminster usually signs all those on the formal review, but if anything comes up afterwards, it's been done on an oral basis, but I don't know. I've never been put in that position. I don't know if Joe has. I don't believe he has.
So the fact that a written decision was requested, as far as you were concerned, was not the normal way to do it.
It was not the normal as far as I was concerned.
And as I recall your testimony, you testified that you made it clear that you would not sign a written statement approving the launch. Am I correct?
Yeah, that's correct. And I think that's been misinterpreted, at least by the press. They said that I was overruled by my supervisor. That's not true at all. I chose not to sign that. He didn't overrule me. I felt that decision I started was an engineering decision by the people that understood the problem the best, that had all of the data and facts, and they're the ones that should recommend it, and that's why I made that. It wasn't I was overruled.
Thank you very much. I'm sure other commission members will ask the question. Mr. Armstrong?
Yeah, you were talking about the 40-degree qualification of various components of the solid rocket booster. And I was aware of the 40-degree limit on the grain bulk temperature, but was there anything else that the 40 degrees referred to?
Well, in the spec, going back after the fact and looking at it, that's what it refers to as the propellant mean bulk temperature. I guess that's, in my opinion, is an oversight maybe in the spec, or the launch temperature of 31 to 99 should be stronger in there to apply to all components. And by qualification, it either has to be qualified by test or some analysis, and that means every element. And I'm not aware that all those elements were qualified for that temperature. I know we bought O-rings that said they're good to minus 30, but I never saw the analysis in the application that we use them in that says that they're good to that. And that's a difference. It's a material problem versus a design problem.
I understand that, and I understand that 4 degrees was intended to protect against grain cracking and the consequences of that, but what I didn't quite understand is why you said you wouldn't recommend any time launching below 40 degrees. I'm trying to get a...
Well, the reason I said that is I felt that's what everybody had signed up to, is what this thing was really qualified from an operating standpoint. Now, the motor does get exposed to much lower temperatures. We have a criteria in our specification expose that to much lower temperatures, sub-zero temperatures and 60-mile winds coming across Wyoming, because we ship these things from Utah down to the Cape. So in a transportation mode, they are subjected to some very severe temperatures for periods of time. And there has been analysis to show that they will withstand those temperatures as long as you don't operate them at those temperatures. The 40 degrees, they won't crack. There's no problem there. That's primarily a performance standpoint. You lose total impulse and performance the lower the temperature you go. If you get below 40, you start losing performance out of the shuttle, and that's why that number came about. As far as the capability, the grain structural capability, it can withstand a lot colder temperatures than that. And we have analysis for the storage and transportation that shows that, and it has good margins of safety, very high margins of safety for exposure to lower temperatures. It's just that things like the O-rings and some of these other components, I'm not aware that we have really analyzed or tested those well enough to understand how they would operate in that kind of a temperature. There's a difference between exposing them and storing them versus operating.
Thank you.
I have a question, just referring back to the static test that you mentioned at 36 degrees, which was used as a justification. Was there an analysis to indicate what the O-ring temperature during that test was?
Well, it was done after the fact, and I believe in the presentation that was made on the night before the launch, they calculated like 47 degrees is what they presented as what they expected the O-ring temperature to have really been when that was static tested.
I have a couple of other questions regarding the conference. Was there a specific request by NASA to reconsider, or was the reconsideration as a result of the implications of the remarks made by the NASA people in the conference?
You mean the reconsideration of what?
Of the launch, of the initial decision not to launch. That is, the initial recommendation of fire call was not to launch, and then that was reconsidered. Did anyone from NASA explicitly ask for reconsideration, or did the reconsideration occur because of the negative remarks and comments on that decision?
Well, I think it was the latter. I can't fully recall whether they directed us to do that or not, that they had concluded that the temperature data was inconclusive, and I don't know whether we volunteered to reassess it or they said we need to. It's not clear to me on that. I'm not sure.
One further question in regard to the signature on the sheet which was faxed from Mr. Kilminster. Was there a specific request for that to be signed, and who made that request?
Yeah, there was a specific request for that to be signed. I believe it was George Hardy. It may have been Larry Malloy, but I think it was George Hardy had requested that.
Mr. McDonald, did you consider bringing your concerns about the final recommendation to the personal attention of Mr. Moore or Mr. Ulrich or Dr. Lucas?
Well, I'm very familiar with the process by which these things are reviewed, and I was absolutely positive and sure that they were brought to their attention, because that's the way things go. I talked to the SRB project manager, I talked to his boss, the shuttle project manager, the shuttle project office, and I was sure that those all went through that review. I had no doubt in my mind that they had.
Thank you.
You indicated that NASA folk indicated that they would pass your concerns along. And I presume that you thought they would, the three concerns that you were talking about, the O-rings, the ocean, sea, and the ice.
Right.
But could they have simply meant the last two concerns, the sea and the ice? That's one question. The other is, who were the NASA folk that promised to pass your concerns along?
I guess you could interpret maybe as I thought it would be all three, but the people were Mr. Malloy and Mr. Reinhardt said they would pass those on, and I presume they'd pass them all on. I didn't see a reason why they wouldn't.
Donald, you mentioned earlier that you thought this decision on launching should be an engineering decision, not a program management decision. How would you characterize the final decision to launch from Thiokol? Was it engineering or was it management?
Well, I guess I'd have to characterize it as a management decision, the final decision.
Thank you.
Got a couple of questions on criticality ones. Did I understand you to say that you chair the board on crit ones on the SRM from Thiokol?
Yes, on all defects that are affected by that, yes.
Could you give us your understanding of the meaning of criticality 1 and just an estimate of how many parts in the SRM system are classified as crit 1?
Well, I don't have a good number for you, but there's a tremendous amount of crit 1s on the SRM, primarily because the motor doesn't have very many redundant features. Solid rocket motors don't. And, of course, a lot of it's structure, and structure is all becomes a crit 1 if it fails.
Could you define a crit 1?
Crit 1 is a single point failure that if that element fails, there's no recovery. You lose the hardware, and it's catastrophic. There's a lot of elements in the SRM that are under that category. Relative to the O-ring seals, the redundancy was built in because that was a critical element as a pressure seal in order to provide that redundancy. I think there is some confusion of late as to what that crit 1 and 1R was relative to the seals and how it was removed. I wasn't involved at the time, but it was found that because this joint rotated, that if you took all of the worst engineering tolerances and dimensions that were allowed by the prints, and that means the maximum clevis opening you could have to start with, the smallest and thinnest tang that you could put into that clevis opening, and the minimum O-ring that you could put in there, with the maximum size of the grooves that you could possibly put in there, that if you put all those combinations together, you could show that you would actually lose squeeze on the secondary O-ring once you pressurized the system and the joint rotated. And therefore, if you ever had to call upon that O-ring as a redundant system during that time period, you couldn't depend on it. Now, I went back and had an assessment made of have we flown any hardware in that condition, because I was a bit shocked about that as much as anyone when I first found that out, which was, by the way, last August. And I made that presentation here at NASA headquarters. I wasn't aware of it myself, that we had such a condition, that we were flying with a crit 1 on that part of the hardware. Based on the information that I have received on all of the joints ever flown on the shuttle, there was only one time where we had a tolerance stack-up of a joint that would have fallen from a criticality 1R to 1, and that was on STS-4. We have never had one since. We didn't have one before that. We always had adequate squeeze from the hardware when it rotates to maintain it as a criticality 1R. Now,
I'm not quite sure I understand that, because I thought that the piece of paper in the critical items list specifically lists the primary O-ring as a criticality 1.
Yes, it does, and the reason it does that is because the drawing tolerances allow you to install hardware that may come together on a worst-case basis that cannot guarantee a secondary seal. And therefore, if you can use all the hardware that's in the inventory, or you could possibly have in the inventory, build to acceptable prints, you could end up with a very small fraction of it. It's a very small fraction that could go together that way, and therefore that document was written to cover all that. But in reality, other than that one case, we've never assembled hardware that way. We haven't had the thinnest tangs with the widest open clevises with the minimum O-rings ever put together. That's a concern, and a seal is a very serious concern, in my opinion, because that decision was made at the time based on what we knew about joint rotation. Since that time, we're getting this information on resiliency and effects of temperature, which were never put into that at that time, that brings that question back out in front. You know, I told you we didn't fly from criticality 1R and 1. Well, that's true based on the decisions and the information is known that changed it from a 1R to 1, just on the tolerances and dimensions. As far as this resiliency thing, I can't assess that yet well enough to know. But I do know we never stacked hardware together that had tolerances so bad that we didn't have contact of the secondary O-ring, other than one joint.
But just to be clear, I guess that you don't, on a joint-by-joint basis, go back to the NASA board and kind of reclamor the Crit 1 and turn it back into a 1R, do you? It's always classified as a criticality 1 on the primary seal.
That's absolutely right. You're correct. Now, we do, as part of our flight readiness review, do present those joints that we're mating and what those O-ring squeezes are on every flight.
Did any discussion of the primary seal as a criticality 1 come up during your meetings on L-1?
No, they didn't.
Okay, thank you.
You suggested that the secondary seal would not be much affected by the temperature, but now you're telling us that because of the complete or nearly complete loss of resilience, that is the tendency to spring back, the secondary seal would require very little rotation to open. Do I understand it correctly?
I said it wouldn't be affected as much as the primary seal because it doesn't have to move from one end of the slot to the other, but as far as the effective resilience, you're absolutely correct. It still has the same problem. As far as extruding in the gap, it's still got the same problem.
We were talking about, somewhere there was a discussion about the secondary seal being redundant until the metal parts rotate. When the pressure starts to build up, it can't move the primary seal until there is some pressure. And then there's a very small pressure, perhaps, and a very small rotation. Isn't it true that the rotation is more or less proportional to the pressure, or is there some delay of some sort?
There is some delay.
So why is there a time delay between the two?
There is some delay because the joint's stiff enough that under certain pressures you just don't move it at all until you have to build up some pressure to make any rotation. So there is a delay in that time period, but at some point in time it becomes a direct function of the pressure.
Isn't the laws of elasticity such that everything is proportional to the force and all the displacements are proportional to the force? Then wouldn't it be true that at every pressure there's some rotation and the rotation is more or less proportional to the pressure?
Well, I think that when you're down to 2 psi or 50 psi, I don't think you're rotating anything.
You're rotating at 1/10 as much as you rotated at 500 psi, is that right?
Well, the structure is so stiff that I can't believe you're rotating at all at 50 psi. You are moving the O-ring seal back into the groove, however.
Just go back to this criticality 1 so that I can understand it a little better. In 1985, a change was made? 83? 83, I guess it was 82 or 83. At that point, it was listed as criticality 1 with an R. Is that right?
That's correct.
Now, does that mean that it was decided that if there was a failure in that seam O-ring, that the mission and the crew would be destroyed, the whole thing would be a catastrophe? But at that point, the R meant that there was a redundancy there, that you had two rings, and each at that point was considered to support the other, or at least one was a backup for the other. That's what R meant.
That's correct. It's redundant. It means redundant. That's why the R is there.
That's right. Now, at that time, the experience fairly demonstrated that the analysis that you'd been using up to that point may not have been correct, so that instead of having both a primary and a secondary seal, which provided redundancy, you came to the conclusion you didn't have the redundancy. Therefore, it was changed to criticality 1. The R was removed. Is that correct?
That's correct.
And so from that point on, I believe it was in, what's the date? December 82. Those shuttles have been flown on the basis of criticality 1, so there was a failure of that seal, a catastrophe would result because there was no redundancy. Is that correct?
Well, I guess that's the interpretation of that, but recognizing the actual hardware that was put together and what we knew at that time, I don't believe that was true. What was true was that the drawings, as I mentioned, allowed a condition where you could fly that hardware in that condition.
But just to be clear, what the SIL says is that the primary O-ring is a criticality 1, and you're not allowed to consider the secondary O-ring as a backup to that.
That's true, Sally. That's absolutely correct. That's what it meant.
And that was known, I assume, by everyone that was working on the program, or most of the top people working on the program. Would that be true?
Well, I kind of thought I was one of the top people working on the program, and I didn't know that until August of 1985 when I put that presentation together. I presume it was. I did find out there was some disagreement between both Firecall and Marshall in interpreting that relative to the joint rotation. The joint rotation that was used for concluding that was obtained from two different sources. One of those sources was from the Structural Test Article 1, first structural test article, and this is way before my time, but where this test article was taken to Marshall, and it's basically a forward segment, it's unloaded now, and an aft segment, where they input both the pre-launch loads, and they put flight loads and all that business into the test article. And this test is run horizontally. The element's horizontal, and they measured through the leak check port, I understand, or some places, the actual rotation of these parts. And got some fairly high numbers, up around 60 thousandths, I believe, is what they said it rotated. We had run some tests ourselves in a vertical assembly during a hydro test and measured some of the rotations and got numbers like 30 to 40 thousandths. So there was some disagreement as to which numbers were correct. Some of our people felt that the horizontal assembly may have made the structural test article numbers not representative. The vertical assembly is better. And in fact, because of that disagreement, we're in the process and started early last summer at the direction of Marshall to come up with what's called a referee test, to do some very careful instrumentation in a vertical assembly to get a better handle on the exact amount of joint rotation. Those joint rotations that are used are those that are predicted for the maximum expected operating pressure, which, by the way, we've never obtained. Fortunately, I hope we never do, but that's a 3 sigma out there someplace. But that still is a point of controversy as to what that number really is, because the SIL, I believe, the critical items list that changed that from 1 redundancy to 1, not only assumed the MEOP, but I believe it assumed the larger rotation, which is about 50% more than some of the data that we got from vertical. So I still don't fully understand that. What I do understand is that it was made at a time when temperature effects were not known. And the resiliency problem that Dr. Feynman brought up, I think, is the more serious one. Going
back to beginning in 1985, when you realized that the criticality 1 was on the critical items list, you knew from that point on that a single failure would be catastrophe as far as the mission is concerned.
Well, as I mentioned earlier, that you have to postulate what your failure mechanism is, and I felt very strongly that the blow-by that we had observed indeed was on the early part of the ignition transient. I think we all felt that way. We've modeled that, by the way, I think fairly reasonably on the erosion. And that at that point in time, when the hardware really hasn't had a chance to rotate, taking the temperature effects out now, that we do indeed have a good redundant seal, because if we lose the primary O-ring at that time, that secondary seal is in a better shape than the primary to really seal. It hasn't come off its land at all if you ignore the resiliency problem.
In a different scenario, suppose that as the pressure is increasing, for some reason, the primary seal, just to understand what the situation is, the primary seal begins to erode, and by the time the pressure gets to some figure like 600 or 700 psi, which is, I think, just below the maximum operating pressure, it finally erodes all the way through so that the gas can pass through the primary seal. Would you think there was a reasonable probability that the whole thing would fail because the rotation by that time is enough that the secondary seal can't hold it?
Yes, I think there was. And that was our assessment in August, that there was a reasonable probability.
Okay, that you first knew or thought of in August 1985.
That's correct.
Not before.
That's correct.
Thank
now,
following up on that, wouldn't you assume that other people who'd been working on the program and working on the seal and the O-rings would understand that too?
Yes, I think there's another important piece of information. Back in the end of April, 85, forgot the exact flight, but it was the last one in April. We had a problem with the O-ring seal and the nozzle. That flight, after it came back, the nozzle was still attached to the aft segment, and we disassembled the segments when they were brought back to the port. And then they're put on rail cars and sent back to Utah. And we never got the segment back until, I don't know, sometime in the latter part of June or something. But this flight was at the very end of April. We disassembled that nozzle. We found that we had violated the primary seal back in 3 locations and burned completely through it. The secondary seal also had eroded like 32 thousandths. But it held and it did its job. That was in a nozzle joint. The primary seal in the nozzle joint is a bore seal, quite similar to the field joint. Tolerances are a little different. But the secondary seal is a face seal. It's, they're both somewhat dynamic seals. This is more of a static seal than the bore seal. The face seal is torqued down with bolts. And it obviously did its job, and our conclusion was, in that particular instance, was that even though we passed the leak check, that the vacuum putty may have masked that leak check. We were using at that time a pressure, stabilizing pressure to run that leak check at 100 psi. We had some data earlier that showed us that the consistency of that putty is quite variable, and you can actually, the putty will become a good sealant in many cases, and it can hold as much as 100 psi for a good period of time. Sometimes it'll blow through, sometimes it won't. So our concern was that maybe we're not really checking the O-ring seals, we're checking the putty. We've got to make sure we're checking the O-ring seals. So we jacked the pressure up to 200 psi. That was the last flight that we were still under the 100 psi, which is the previous requirement. To stabilize it at 100, and then once you stabilize it for a period of time there, you drop the pressure completely again, you bring it up to 50 psi, and that's what you run the leak check at for about 10 minutes. You only allow 1 psi drop. On that particular set of hardware, since it was the last one we ran with 100 psi, because the change hadn't gotten through with all the paperwork system on what we understood about what putty behaves under pressure, because we went to 200 psi for the field joints at that time, just hadn't gotten the nozzle. we concluded that the putty may well have masked that leak check as it was at 100, and therefore we may have had some defect in that seal that we didn't detect. And as a result, that seal leaked at ignition from time 0. And when that happens, you get severe erosion on the O-ring because you get the jet impingement that we've been calculating, which is direct onto the O-ring seal, like a flat plate. But when you bypass the O-ring in a leak like that, it actually chokes at that point, so you're forming a throat, and it erodes very rapidly from underneath as well as jet impingement, and you lose quite a bit of the seal. We lost most of the seal, in fact. But the nozzle seal is very good, the secondary seal, because it's around the corner and expands, goes down around the corner, and eroded some of the secondary seal. We ran a lot of analysis after that because that was the first time that we had observed erosion of a primary seal. We developed our models to predict the erosion, what would happen in blow-by erosion, and it was because of that that we found that hardware, and it was late in June, it was into July that we got all that data together. We went down to Marshall and had very detailed reviews because that was a serious concern to everyone. We had violated the primary seal. It was in the nozzle joint. That we were asked to come to Washington, to headquarters, and review that. It was a very serious concern. It was that time that I got with the engineering people and said, we need to not only put that whole story together, we need to put the whole story together on all the pressure seals, because I and several others still felt that even though that problem happened with the nozzle, the field joint was a more serious concern. Because I felt very good about the secondary seal in the nozzle. I didn't for the field joint. And I put together a presentation for August that I think showed where our real concerns were and why we felt the highest priority was a field joint, even though we just experienced that problem with the nozzle. We felt we had corrected the problem with the nozzle because all subsequent flights had the 200 psi leak check so that we could not miss a possible defective seal or contamination that may have prevented that seal from sealing in the first place. But that was some of the background that I think really turned up the game on the whole seal issue from about April, really in June on. Prior to that time, we were doing a lot of work to better understand this rotation business and all. But we have done a tremendous amount of work. In fact, you may have read in the press, and it's true, that we actually went to a SAE conference last fall. A couple of our top engineers went there to try to get help from the whole seal industry and the SAE about seal joint. Is there a better way to seal that joint?
What is SAE?
The Society of Automotive Engineers. And we did a lot of work to try to get help from the outside as well as do the work that we had inside. And I think that's all relevant to the discussion.
Were you surprised that some of the top people in the decision-making process didn't know about this at all?
Didn't know about the CIL or the criticality one or what?
Well, the whole thing, the concern on your part and on the part of ICOL's engineers that the original decision had been not to launch and all of that.
Oh, I'm very surprised at that. I hardly believe that. The issue was so controversial, I thought that I'm sure that they were aware of that. I have a hard time believing they didn't.
Could I ask one question? In talking about criticality 1 going to 1R, I think you made the comment that you'd have to have all of the tolerances going in the wrong direction to meet that condition. But you did say that one unit did meet that condition.
Yes, best of my knowledge, and I had some record search done, that I was told that there was a condition in the, I think it was forward field joint of the STS-4 someplace that was in that condition.
Well, what if that launch had been done at a cold temperature? Wouldn't it have maybe taken it over the edge?
I don't know. It's possible. I certainly don't feel good about that. But.
Well, the reason I asked the question, it seemed to me that if it was a criticality 1 item, then everybody should treat it as criticality 1 and not rationalize that it may not ever happen.
Well, I agree with that.
And do you think everybody else agrees with that?
Well, I think, yes, our engineering people agree to that, and that's why the recommendation we had made originally was the basis for that recommendation. We felt that we had observed a condition a year earlier that we did feel was attributed to temperature in some way or another, and it was not a good condition, and we didn't want to go much beyond that because even though that one was successful, it certainly wasn't a good condition.
Was it at was it NASA or Thiokol that originally initiated the change from criticality 1R to criticality 1 for the primary O-ring?
I have to tell you, based on what I was told, because I wasn't involved in that change, but I was told that that was NASA initiated.
What experience led to that change? Do you know?
I'm not sure of what experience led to the change. I presume it was the understanding from the joint rotation data and the drawing tolerances of all these parts that that condition could exist someplace in the hardware, and therefore if we were going to fly the hardware as it was designed, that either through refurbishment or new hardware that was within those tolerances may be matched together sometime to give us a condition like that. But I think you'd have to ask the people that were involved in that condition.
How do you account for what appears to be the fact that between December 82 and the middle of 85, when Thiokol became concerned about the erosion of the blowby, that flights did not occur seemingly during that time that led to the same concern?
No, I can't explain that. I certainly didn't know about it until August 8th. I don't know. I think that everyone was concerned, at least from the standpoint that we always had to present data on the joints that we were mating to show we had adequate squeeze and all. That data was presented, and I'm sure people were concerned about that.
Thank you.
For questions, we'll have a 10-minute recess. That was a good presentation. Take the stand. We've got the model of the Mr. Mason, you requested that you appear after Mr. McDonald, and we'd be glad to welcome you and go ahead and proceed any way you'd like.
Thank you, Mr. Chairman. We've given you a handout there, and I wanted to start on page 18. We had originally thought to provide some technical background, but that can be covered later. On page 18...
Could I say, we have, of course, have received quite a lot of this information in executive session, and we will certainly be pleased to look at the information on these first 18 pages. But proceed in any way you like.
Okay, thank you. My intent here is to explain the organization structure and those people that participated in the discussions, and then go through the chronology of the occurrences that night on the 27th of January. First off, I'm the Senior Vice President of Wasatch Operations. We have, on the chart you have there, selected only those people that participated in the discussions. But I might point out that there are 3 divisions reporting to me: the Space Division under Mr. Wiggins, who is listed there, and there are also a Tactical and Strategic Division reporting to me. Mr. Lund, who shows there as Vice President of Engineering, provides engineering services for all of our all 3 divisions. We've covered just the Space Division in detail, you'll see that Mr. Kilminster reports to Mr. Wiggins, and he's the Vice President of Space Booster Programs. And of course, you've just heard from Mr. McDonald, and reporting to him are Mr. Ebling and Russell. And then from the KSC office is Jack Buchanan, also reporting to Mr. Kilminster. Within the engineering organization, there's a Space Shuttle Project Engineering group under Mr. Brinton, and Mr. Macbeth reports to him. Then the other part of engineering, engineering design organization, you'll see the people listed there. I don't need to read them, but they were all participants in the discussion. We added a couple of notes here we thought were pertinent. One is that we do have a flight readiness review at Morton Fire Hall before Marshall has their flight readiness reviews, and Mr. Wiggins chairs that flight readiness review group. And the results of that flight readiness review are signed off both by Mr. Kilminster and Mr. Brinton to indicate that we're ready to fly. And then Mr. Kilminster then attends the flight readiness reviews of NASA. One other point we made here, which was also discussed by Mr. McDonald, and that is that he and Mr. Kilminster have been alternating as the attendees at the launches. Now, as I go through the chronology, you'll see the names of various people here, and you'll find them all in this chart, but I will try to point out where they fit as I go through the chronology. We have the times here listed both in Eastern Standard and Mountain Standard Time, and the significant occurrences as we move through it. At 1 o'clock Eastern Time, Mr. Macbeth and Mr. Arnie Thompson and Charlie Saderholm all received calls from Boyd Brinton, who was at Marshall. And that's something I ought to point out, that throughout this discussion, Mr. Brinton, who is the manager of Space Shuttle Project Engineering, was at Marshall Space Flight Center, as were Mr. Speed. And then, as you know, Mr. McDonald was at Kennedy, as was Mr. Buchanan. The rest of the people that we have listed here then were all at the Wasatch in Utah. As a result of the call at 1 o'clock, Mr. Ebling and Kentner were notified, and Mr. Saderholm started a bulk temperature analysis of the propellant, and Brian Russell arranged a meeting in Mr. Ebling's office. They convened that meeting in Mr. Ebling's office, and the attendees are as listed there. During that meeting, they discussed the O-ring resiliency data at 50, 75, and 100 degrees. They talked about the amount of blow-by and erosion that had been seen on the 51C, which was the previous coldest launch.
Were you at those meetings?
I was not at that meeting, no, sir.
So this is hearsay as far as you're concerned?
That's right. I do get to where I enter the picture here in a moment. This was an effort to get an overview of what happened and where, to try to make the rest of the testimony flow a little better. They did look at the other launch in static test temperatures and concluded that they did have a concern. They broke that meeting up and started to do some work. Mr. Ma was to run the calculation of what the O-ring temperature would be if the ambient were 18 degrees. And Mr. Ebling notified Mr. Kilminster of the concern that they had. And Mr. Kilminster asked Ebling to get the engineering management, including Mr. Lund, involved, and to notify both Mr. McDonald and Mr. Brinton of the Marshall concern.
So I assume that there was no recording made of these meetings. This is reconstructed from conversations you've had with other people.
That's correct. We did talk to all the people involved, so we felt we had a consensus of the sequence. Then Mr. Buchanan called to give us some temperature predictions. At that time, they were predicting 34 degrees at launch time at 9:38. Then Mr. Thompson briefed Jack Cap on his concerns. Then Mr. McDonald called from Kennedy hoping to have a telecon between Morton Thiokol and NASA on those concerns. There were people called to the conference room to support the telecon, and that required interrupting the meeting that was at that point underway in Mr. Lund's office.
Well, just for semantics, you say people called to support telecon, you mean to take part in the telecon?
Correct. The conference room we have there has microphones so that you can be in the conference room and anyone can talk and be picked up their conversation.
My question really has to do with the word support, where you say your conference to support telecom and interrupted to support telecom. You mean take part in the telecom?
To take part, that's correct. Correct. That conference or telecon then proceeded with the people that are listed there, some 13, including the people at Marshall and at Kennedy. At the time that started, they notified Mr. Kilminster that we were starting. At the same time, essentially, he received a call from, that LSS means Launch Support Services. That's the people that work for Mr. Buchanan down at Kennedy. They called and gave him an updated overnight temperature predictions on a 2-hour basis. Every 2 hours they gave him what the temperature was going to be. So,
were there any notes or records kept of this conference? Is this all reconstructed from memory?
Well, I don't know of any specific notes, although there may be. Guess I have to answer it that way. I know the calculations that were run. Those calculations exist because they took those on every 2-hour basis and had started using the 18 degrees and then proceeded to use the more updated temperatures, because ultimately we were told it was forecast to be a 29-degree O-ring temperature. In any event, those concerns that existed were discussed, and they amounted to the fact that the previous coldest launch had given us the greatest blow-by, and that coupled with concern about the cipher O-ring that would exist at a lower temperature was the focus of the discussion. It was just that, a discussion, and so it was decided and NASA requested that we put together an organized analysis and organize the data and write down what our concerns were so that it could be reviewed in a more careful fashion. So there was a telecon then scheduled for 6:15 to do that. And at that point, Mr. Kilminster called Mr. Wiggins and me. We were in another meeting in our Brigham City plant, and told us that there were concerns and that the telecon was going to start at 6:15. So we hopped in the...
Good question.
Yes, sir.
You had data where you reached a conclusion. What was the purpose of NASA asking you to better organize that data? Was that for them to review it and reach some of their own decision, or just to see if your thinking was proper?
At this point, we had not reached a conclusion. During the part that I'm covering here, we'd had the discussion.
I still don't understand why they needed the data better organized at this point in time.
We were providing it verbally over the telecom. They didn't have it in front of them. Okay. So we were talking about things like curves and that sort of thing that they didn't have the direct visibility of. And we had not yet reached any conclusion. We were just saying that we were concerned because it was cold. So the request was to get that data and fax it down so they could look at it at the same time that we were looking at it. And then when Mr. Wiggins and I were notified, they were in the process of putting together what data was needed for the discussion. And at the same time, Mr. Lund was trying to prepare some conclusions and recommendations. So the chart preparation and the conclusion recommendations were going on simultaneously. And Mr. Lund, or Mr. Wiggins and I then arrived as that was going on. And as it turned out, we were not able to get all the charts together in time to start the telecon. We got the first charts faxed down there by 6:30, and the last charts didn't get down there till 7:20. So we were working this in a real-time basis. We did start the discussion again at 7, and the engineers that had prepared some of the charts discussed their charts, and then ultimately Mr. Lund discussed the conclusion and recommendations chart. The fundamental issue, however, was the concern about what effect the cold would have on getting the primary O-ring to move into its sealing position and seal. And if it needs clarification later, Mr. Lund has some charts to explain that. But when we run the leak test, the primary O-ring is moved into the furthest point away from its sealing position, and that's maybe 20,000ths of an inch or so, whereas the secondary is moved towards its sealing position. And the concern was whether the cold, the stiffness of the O-ring and the grease would delay the movement of the primary O-ring so that it would not seat properly, and there would be blow-by and perhaps damage to the secondary O-ring. We looked at the erosion history we'd had to see what correlation there was with temperature, and there really wasn't any correlation. There was also a review of the blow-by history, which Mr. McDonald's covered very well. And the correlation that appeared there was that we had blow-by in both 75 and 53 degrees, but it was much more severe at 53 degrees. And so it was thought that that was evidence that the cold did in fact affect performance of the O-ring. Now, we looked at data on the hardness of the O-ring, and as an indication of how stiff and difficult it might be for the O-ring to move. And we determined that from 50 degrees to 30 degrees, a 20-degree drop, would increase the hardness by about 10%. In fact, that put it in the range of when we discussed this that night. Early in the program, we were deciding what hardness we wanted, and we had used some 90-durometer O-rings in some of the hydrostatic tests. We ultimately ended up with the 80-durometer O-ring. But it was pointed out that we'd had some experience with that O-ring, which was harder. Then...
what you mean by hardness is it's difficult to wash it into the tiny crack that it's supposed to go into? What is the feature that hardness? It's not resiliency. It's the difficulty of pushing it into a corner?
Yeah, well, it was thought that that stiffness might make it move more slowly, moving across the gap, and then it would be harder to extrude it in. However, once it's sealed, the being slower to extrude per se wouldn't be a problem once it's sealed. The points we're talking about, of course, were the points that were discussed back and forth that night. We did look at the temperature history on our previous tests and flights, and we discussed the fact that we had run a subscale blow-by test at 30 degrees, which had shown no blow-by. That was only an indicator because that was a cold test and it was with a fixed joint gap. So it was just another point of data that we had to put in our heads.
Mr. Mason?
Yes.
Is that a vertical or a horizontal test rig that you ran the subscale test on?
I don't know.
Could you find out for us, please?
Yes, sir. There's several fellows there know, I'm sure.
Just a vertical test rig.
Vertical. Out of that discussion, we got to the point where we couldn't make a clear conclusion of the effect of temperature on the O-ring performance. And a number of the engineers felt that on that basis that we ought to just stay where we were in our flight history. And with the information we had at that point, and as far as we had proceeded in our thought process, that appeared to be the right thing to do. So we proceeded to present that information.
Isn't it fair to say, though, that all of the engineers felt that way?
No, sir.
Which ones favored?
At that point, it was not a pro-con sort of discussion. It was, where are we in our thought process? And where we were in our thought process was that what we've discussed to date says, let's stay with our experience.
But,
and
what I mean is, didn't all the engineers agree with that?
I would say that at that point, we all agreed with that.
That's right.
That it wasn't engineering or anyone else. We just had looked at what we had and went through our thought process, and at that point, we felt that was the recommendation.
And the position that you took unanimously was the engineering position was to base recommendation on previous flight history, and you cite 51C, which was the coldest launch that had been made and where you'd had the most trouble. Isn't that right?
That's right. The next comments then were essentially as Mr. McDonald said, that Mr. Malloy said he disagreed because he didn't feel that we had shown any correlation between blow-by and erosion with temperature, and that therefore the rationale that had been used when we decided to fly in the first place was still a valid rationale. And Mr. Hardy expressed surprise at the recommendation because it was above the qualification temperature. However, he said he wouldn't recommend flying against our recommendation. And then Mr. McDonald came on and said that he too had concern about the cold, but he pointed out that the secondary O-ring was in the position to seal where it didn't have to move as the primary did, and at this point ought to be considered. With that discussion, we were let's say we felt that we needed to have further discussions to see if these comments would in fact cause us to have any change of our position. And so we decided to do that off the net, and we asked for a caucus. Now, in the caucus, we revisited all of our previous discussions, and the important things that came out of that was that, as we had recognized, we did have the possibility that the primary O-ring might be slower to move into sealing position, and that was our concern, and that's what we had focused on originally. The fact that we couldn't show direct correlation with the O-ring temperature was discussed, but we still felt that there was some concern about it being colder. We then recognized that if the primary did move more slowly, that we could get some bovine erosion on the primary. But we had pointed out to us in that caucus a point that had not come across clearly in our earlier discussions, and that is that we had run tests where we deliberately cut large pieces out of the O-rings to see what the threshold of sealing was. And we found that we could go to 125 thousandths of a cut out of the O-ring, and it would still seal.
Mr. Mason, is that a static test or a dynamic test?
It's done by blowing the pressure against the O-ring, and it was done both cold and hot.
But not in a moving joint?
That's correct, right. And I might follow that. Through the whole discussion, we were concerned about we recognized that the O-ring, either primary or secondary, would have to seal before the joint had a time to expand. Now, the gas pressure gets to the O-ring before the joint has a chance to expand, but the question was, with the slower movement of the O-ring, would it still be there and seat before the joint expanded?
Mr. Mason, what kind of a time frame are you talking about here and the time it takes to get there?
Well, the charts that we had said that if you seat in 160 milliseconds, that, well, let's see, this goes back to that 1R1 discussion that we had. And what that boiled down to was that during the first 160 milliseconds, the joint is still closed enough that the secondary O-ring actually provides redundancy. Up to 103 or up to 300 milliseconds, there's less certainty, and above that, there's a serious question about that. Now, again, that chart was based on the worst conditions as far as joint conditions were concerned, that's tolerances. And what we had here we knew was a fairly nominal compression condition.
160 milliseconds, that joint is officially classified as a criticality 1R?
It's not officially, no ma'am.
That's right, it's just a criticality 1. So even during the first 160 milliseconds, you are not allowed to consider the secondary seal a backup to the primary seal by the critical items list.
Well, I don't certainly want to debate that point. What we did is what we considered. We did consider that when it was established that it went from a 1R to 1, it was identified that we were losing redundancy after the ignition transient. And we did consider, and that is where I'm headed, that there was some protection during the ignition transient from the secondary O-ring.
I'm not sure I understand your answer to Dr. Wright's question.
Well, let me try again.
It sounds to me like to exercise some kind of engineering judgment on whether you can consider this a 1R or a 1. And I just don't think that the system allows that. I think that once something is classified as a criticality 1, that sets a red flag in everyone's mind that that's an extremely dangerous situation. And I'm just not sure that you're allowed to go back and rationalize it as, well, during this 100 milliseconds we may have a secondary seal. We may be allowed to consider it a redundant seal. We may have protection to a criticality 1 system.
Well, I really can't address the propriety of it as far as the system is concerned. I'd have to state what we did, and we had recognized when the criticality was changed from 1R to 1 that it was done because we didn't have a full-time redundant seal. And at the time of this discussion, we were not addressing the thing from a 1R1 viewpoint. We were addressing it from what we knew of how the joint performed. And what we knew was that early in the ignition transient that the secondary, in fact, did function until the joint rotated. Now,
but isn't that in effect changing the critical items list? I mean, the authorized says that the list shows that there was no redundancy, and if I understand your answer, you're saying we as a management team decided there was redundancy.
We did consider that as a factor in our decision process, and I need to let me say first I didn't get to the thing in the right sequence. Our primary concern and the thing we addressed in our earlier conversation was making sure the primary O-ring would seal. And when we had this further discussion, it was pointed out that we had run the test which showed that we could tolerate about 3 times as much erosion in the primary O-ring as we had previously experienced. In fact, experienced in the 51C, I should say, in that cold test. So we felt that we had a substantial margin because we had the ability to tolerate much more erosion than we had, and that the erosion was driven by the volume of gas that could be passed that O-ring, and that we felt was limited, so that it would very unlikely that it could get beyond the 3-time erosion beyond the 3 times the erosion we had seen before.
Can I ask some questions? Doesn't the erosion partly depend upon the speed of the gas, the size of the hole through which it comes, and other matters? Do you have some kind of calculation that shows that you couldn't get more erosion than the amount that you got in 51C?
I don't know whether we have that calculation that tells us what that limit is or not.
What made you think that 51C was the maximum erosion that you could reasonably expect?
We didn't say that. We didn't feel that was the maximum we could expect. We said that if there was a temperature effect that made it move slower, we might get some more erosion, and we felt that the factor of 3 times was not likely to be exceeded.
Well, let me explain. I'm not interested at the moment in the temperature. I'm going to criticize the original decision that you could operate at 53 degrees, which is a different point of view than what we're talking about. Based on the idea that you've already seen that you have 1/3 the amount of erosion necessary to split the primary ring at a time when the secondary has a high probability of not being seatable, as Mr. McDonald said. And I'd like to know how you judge, by having seen 1/3 of an O-ring disintegrated in one flight, that it's very unlikely that you would get 3 times that erosion on another flight on the same circumstances.
Well, that's the judgment issue that we finally got down to.
try and understand your judgment.
In our judgment, when we had the previous erosion, to get that, we had to fill all the cavity that was there, all the annular cavity. So there wasn't any way to get any more gas flow.
Doesn't it depend on the speed of the gas and the temperature? Doesn't it depend maybe on the complexity of the blowhole that goes through the putty? So that it would be a matter of accident, how much you got? Could it, for example, have been that you got 1/3 the amount of erosion, for instance? Because the putty hole is smaller and longer, with a reasonable probability?
Well, the engineers which are here I don't have off the top of my head the numbers, but we did run tests with focused jets. Focused the most amount to see how much erosion we would get. And I believe they can do a better job of correlating that than I can. I can comment that my understanding of it was that it would appear that because there's a limited volume, and we had looked at what a most highly focused jet would erode, that the combination of that knowledge made us feel that the probability of getting 3 times the erosion was very unlikely.
Thank you.
Isn't it true that the amount of erosion you can tolerate actually depends on the particular rocket motor you're dealing with, because the amount of compression can vary on a particular O-ring depending on where you are within the tolerances of the two pieces which make up that rocket motor. Had you analyzed the particular amount of compression on 51L, these particular joints, to see whether or not that was the average amount of compression and how much erosion of the O-ring you could actually tolerate?
Yes, we did look at the compression on that particular joint, and we compared it, as a matter of fact, to the compression that we'd had on the previous cold launch. And the compression was essentially nominal. As I recall, it was around 40 thousandths. So we did consider that.
This for just a second. We've got a criticality 1 system, and there's some question in your minds whether it'll perform at the temperatures that are predicted at launch, around 29 or 30 degrees, is what you're basing your judgments on. What test data did you have to show that, or any test data at all, on joint rotation or the timing function or even seal erosion down at 30 degrees that would allow you to make a reasonable engineering judgment that this criticality 1 item was safe to fly?
Well, it was the various items that I mentioned. We had the durometer of the O-ring down to below 20 degrees. I don't remember exactly, but it was down well below the temperatures, and we could see what the change in durometer was with temperature. We did have the 2 tests we had run with the fixed joint at 30 degrees to indicate that the O-ring would seal if it moved in the right timing.
But you said that at the time you weren't putting much emphasis on those tests.
Well, we were
for one
trying
thing,
to.
they were fixed plates, and for another thing, you were using the argon gas, not the freon, by that time.
We were trying to avoid overemphasizing that test, is perhaps a better way to say it. We wanted to make sure we recognized that it wasn't a totally representative test because it didn't have the joint rotation. On the other hand, we felt because it was at the temperature and did indicate that the O-ring would seal if the timing was proper, so that the O-ring was in position before the joint rotated, we expected the seal bed.
Did you have data that would show you how the joint would rotate at those temperatures?
Well, we know how the joint rotates, and I don't believe there's any real effect of temperature on the joint rotation. If anything, it would slow it down.
Had that analysis been done?
The joint rotation analysis to see what the temperature effect on joint rotation is, I do not believe that's been done.
How about the any tests or analysis to determine what the timing function would be at those temperatures? Had those been done at the time?
Well, it had not been done at the time. We were in the process of devising a test to try to establish that.
So those tests hadn't been done when you made this decision?
They had not been done. Well, I better not go beyond my knowledge on the subject. I don't know personally how far we'd progressed in the timing test. I can say this: we didn't have enough information that we could quantify the effect of the cold.
Okay. You said that your previous you had a factor of 3 safety in seal erosion. That sounds to me like you were willing to accept damage to a criticality 1 system. Did you have any prediction of what the seal erosion would be, or any, again, test or analysis on what seal erosion would be under these conditions? Or were you extrapolating from the 53-degree temperature? And did you have a model to do that extrapolation?
Well, that's a lot of questions. We had done some modeling of the flow in the flow effect on the O-ring, and I'm not qualified to really talk about that in detail, but the engineers, when they get here, can provide more detail on that. I've lost track of try to answer all of your questions, and I've lost track. Could you ask me again?
Okay, the first one I guess I was asking about was the seal erosion. Do you know whether you had any test data on the seal erosion?
Well, I know we had a lot of information, as I said, where we had focused, deliberately focused hot gases to see how fast it would erode, what kind of gas flow rates were necessary. And that's on erosion. So
let me ask a different sort of question. Were you willing to accept damage to a criticality 1 system? It sounds as though you were willing to allow erosion on the primary O-ring.
The answer has to be yes. Now let me explain that the position we were in is that the first thing that has to happen is you have to have a blow hole through the putty. And our experience is that happens like 5% of the time. I don't have that number exactly, but if you look at our history in the flight motors, that's like 5% of the time. When that happens, you can either get no effect, just simply the hot gas pressurizes the O-ring, or you can get blow-by and then the O-ring seats, or you can get erosion. And we had erosion, if memory serves me, 4 times in the some 144 joints that we'd had. So we recognized that we might get some erosion. We also recognized that it was a low frequency event, and but that the possibility existed, and that if it did happen, we had erosion, that it would, in our opinion, seal, because of the extra margin that we'd identified by running the tests on the amount of flow it would take to get enough erosion to actually keep the primary from seeding.
I guess what I'm really trying to understand is whether you really had the engineering data or an engineering analysis to back up the decision that this criticality 1 system was safe to fly at those temperatures. You know, what we've seen in the chart so far is that the data was inconclusive, so you said go ahead. No,
yeah, I'm sorry. I hope I didn't convey that, but the reason for the discussion was the fact that we didn't have enough data to quantify the effect of the cold, and that was the heart of our discussion: is how much effect is the cold going to have on the performance? And
a question. your engineers, with the data they had and with the concern the temperatures, did reach a tentative conclusion at least that why not wait for at least the temperature that had already been flown. I guess you were responsible, your engineers were responsible for the design and the testing and qualification of that design, and I would assume the interpretation of the data. And therefore I'm extremely puzzled why a NASA person could disagree and ask you to review the decision your engineers had reached, since it seemed to me theirs was the responsibility for the design.
Well, let's say the request to reassess was not a major factor in my view. The fact that we were picking a temperature based purely on the one test or the one flight, and we had static tests at other temperatures, and Mr. McDonald explained why we didn't consider those conclusive. But it was difficult to say that 53 degrees was exactly the temperature that you ought to fly at. And when Mr. McDonald made the point about the secondary O-ring being in a favorable position, we felt that it was appropriate to consider that point. And that's the reason that we said, well, let's make sure that we've considered everything. And the two things that came out of that assessment were, one, that we believed that we had a substantial margin of allowable erosion and still have that primary ring seat and seal properly. We didn't know for sure that what the effect of that cold was on the time to move. But we said if, in fact, it does delay moving and it causes blow-by, then the secondary ring is already in position. The blow-by has to occur, if it occurs immediately. The blow-by occurs on pressurization. And so under those conditions, if you were to have blow-by, you would be seating the secondary. Now I understand the point about the 1R versus 1. I simply have to be honest and say that that's the way we were looking at it then. That during the ignition transient, that the secondary really could function. And we had never said that it couldn't function on the ignition transient, even when we wrote the CIL, we'd indicated that. In any event, we did expect the primary to seat. We expected the seat because we had some tolerance on this ability to erode and still seat and seal. So that was our thought process. Now, the discussion was a free, open discussion with all of the people there. And I believe that it was not at that point it was clear to me we were not going to get a unanimous decision. And so the question was, did we have a reasonable position to go to 53 degrees, or did we have confidence that we could fly with a 29-degree O-ring? And the people that were there had heard all the discussion, so I concluded it was appropriate to get a poll of the chief engineer and the chief program manager and Mr. Wiggins, who has a division responsibility, to see how they felt, whether they felt that we could safely fly with all the information that had been presented. And we did conduct that poll, and then we did conclude that it was safe to launch.
Could you tell us what the poll showed? You say that you and Mr. Kilminster and Mr. Wiggins and Mr. Lund were unanimous. How about the others?
We only polled the management people because we had already established that we were not going to be unanimous.
And we'd already heard...
That wasn't the question. The question is, what about the others? You testified before that you thought probably all the engineers were against the launch. Now you say you took a poll. You only polled the managers? You didn't ask the engineers how they felt after the review of the data?
In that discussion, I felt that everyone had represented their opinion, and there are a number that I felt indicated, as we did, that with the consideration of the erosion margin and, well, the very factors that I just talked about, that they also considered that to be a reasonable...
No, I'm trying to get... Did they express change of mind? Did they say, well, I've changed my mind?
Not per se, no.
Okay.
But excuse me, I just feel that it's the kind of discussion that we frequently have in which all of the people express their opinions, and they make them clear.
Did you ever have an experience where all the engineers voted one way and management voted the other?
That wasn't the case here.
Well, what was the case here? It looks that way. It looks as if you said the managers you polled were unanimous, and the engineers who were opposed to the launch were still apparently opposed to it.
Well, there were some engineers.
Which ones?
Mr. Boisjoly and Mr. Thompson were the outspoken ones.
No, I'm asking which ones changed their minds. Before you testified that all the engineers were opposed to the launch. Now you went through this process you've just described at the commission. My question is, did any of the engineers change their minds? And if so, which ones?
Well, let's say I would say then that I have to look at the list here. I can, based on the conversations that we had there, I felt that Mr. Macbeth and Cap were supportive, and Mr. Brinton, who was at Marshall, it's harder to judge because he didn't have a lot to say. What we were faced with is that there were the outspoken individuals, and the rest participated to a lesser degree, but I believe that we are familiar enough with the people and their manner to be able to judge their feelings, and we heard what they had to say.
Mason, earlier in testimony in private session, you indicated that Mr. Boisjoly and Mr. Thompson were the most knowledgeable on the seals. Is that correct?
Yes.
Then the two most knowledgeable engineers were still opposed, and my understanding is they were still strongly opposed. Why did you proceed in the light of your two experts being very strongly opposed?
Well, it's kind of a horse race as to who is the most expert on the subject, because there are different areas of expertise, some in the gas flow, some in the metal parts. We identified that Mr. Boisjoly and Thompson were both generally knowledgeable people on those joints, and they were people that whose opinion we regarded. However, Mr. Cap has a long history on the joint, and he's as knowledgeable, in my opinion, as they are. And Mr. Sayre to a lesser degree. So I would say that we felt that although they were outspoken, we listened to their reasons more than the intensity. And the reasons boiled down to the things that I said. The reason was the uncertainty about the rapidity with which that primary would move. So,
did Mr. Russell participate in the conversation either on the telecon with NASA or in the caucus offline that followed?
Yes, he participated in the both discussions, my recollection.
What were his views as far as you can reconstruct them? I felt that he had the similar thoughts that we did. He had the concern about the uncertainty, but beyond that, I would say that he was, if anything, neutral. That he was providing all the information and was having some difficulty, as were the rest of us, trying to get a decision in which we had confidence.
Now, during the telecon with NASA and during the private caucus offline, did anybody, either at NASA or at Thiokol, mention the change in the critical items list to criticality 1?
No, sir. That was not discussed. That was not an issue at that point.
A question about the temperatures. You said that you decided that 29 degrees was safe to launch. Did the discussion result in some lower temperature limit below which you would not have recommended a launch?
I'm sorry, you're saying would we?
Your ultimate recommendation to NASA was that it was safe to launch, and I believe the predicted temperature of the O-rings was 29 degrees.
That's correct.
Did your discussion result in the establishment of a temperature below which it would not have been safe to launch?
No, we didn't pursue it below that. I think that the initial concern when we had heard 18 degrees and we were thinking that the O-ring might be that cold, that's how all the discussion got started. And there was a lot of apprehension at 18 degrees. And then it later found it was going to be somewhat warmer than that. But we didn't pursue the idea of getting any colder than 29 degrees.
Well, how critical was this? If the temperature turned out to be 28 degrees, would this have made a big difference? The recommendation was based on a prediction, but of course that was only a prediction at the time. And I would have thought that the recommendation would have been more specific, so that depending on the exact conditions which prevailed when the launch occurred, the recommendation would have been one which could have been used to make a decision.
Well, I can't argue with that reasoning. We just simply didn't address. We were addressing the specific condition and not looking for a threshold.
But usually engineering decisions and calculations are pretty exact calculations, and you usually have a very specific number. That's why there are launch criteria, and those numbers are specific numbers. They're not ranges. And here, evidently, you had a range, but you didn't even specify what that range was. Wasn't that rather unusual?
Yes, I would say that was. The fact that we were focused on that at one point, and that's what we were addressing. Normally, if you were earlier preparing for another launch or something, if the question came much up, you would in fact tend to bracket it. We were faced with this. We felt a specific condition here, and that's the reason we addressed it that way.
So you didn't feel uncomfortable with this position?
I didn't. I felt that after we had hashed it out and understood it, that the inability to precisely quantify the movement of that primary O-ring was the concern that we had. But and that's the additional knowledge that I would like to have had. But I felt that with what the things that I've already pointed out, that we had a reasonable basis for feeling it was a flight. It was
Mr. Mason, you used the word uncertainty 4 or 5 times now in the last 5 minutes, and now you just had the inability to quantify this thing, and that was the best thing you had going for you. You know, every launch has a risk, but you take that risk because something must be achieved. What was driving you here? What was to be achieved that caused you to go?
Well,
why couldn't you wait a day?
Well, as far as waiting a day is concerned, we wouldn't have gained any more information. But
you'd have gained temperature. You had uncertainty.
That's true. That's true. And we had to decide whether we felt that it was safe to fly at 29 in order to respond to the question, should we fly? That was the question that we were trying to answer.
In responding to the general's question about the use of the word inconclusive and uncertainty in your whole presentation here today, you are basing your decisions on inconclusive and uncertain information, yet my understanding of NASA's flight philosophy is that decisions to go or no go are based on certainties and conclusions. When did this change in philosophy affect your operations?
Well, I would have to respond. I think it's a case of degree of uncertainty. There's always...
Well, do you allow any degree of uncertainty before you launch?
Well, I believe that in any case, in the design and the testing and so forth of the whole system, there have to be some uncertainties. It's a question of degree, and
but it seems to me there was a high degree of uncertainty in your calculations here.
Well, there was,
according to your own testimony.
Well, that of course is the point that we were struggling with that night, was what degree of uncertainty is there. And the area of uncertainty was the moving of that primary O-ring.
Well, how would you characterize it? As a high degree, a low degree, or a medium degree of uncertainty?
As far as the probability of seeding is concerned, I thought there was a low degree of uncertainty.
Mr. Kilminster, when he wrote the telefax, said temperature data not conclusive on predicting primary O-ring blow-by. Isn't that a very serious statement? Just saying that it was not conclusive? Isn't that another way of saying that there might be a conclusion that there was going to be primary O-ring blow-by?
Well, what we did was say, since it wasn't conclusive, we were going to assume that it would have a negative effect. That's the way we approached it.
So in other words, this is a statement saying we expect primary O-ring blow-by.
We said we can't tell how much effect the temperature is going to have, so we better look at what can happen if in fact it does.
Now if that's the case, then Dr. Wright's question is most relevant, because the critical items list said that you cannot rely on this redundancy. If you're predicting there's a possibility of primary O-ring blow-by, you're violating the critical items list.
Well, and we weren't predicting it, but we were saying, because we weren't able to be certain, that the situation we were faced with is we have had blow-by on earlier flights. We had not had any reason to believe that we couldn't experience it again at any temperature. That's where we were right then. And so we had to say that we can experience blow-by because we had experienced it, and we had not yet been able to figure out what to do to prevent it. So we knew that it could happen, and so we had to say, what's the probability? But even given a low probability, we still had to think, what's it going to mean if it does? And that's what we endeavored to do, was to think, what does it mean if it does, even if it's a low probability?
Well, I don't want to continue the argument. It seems to me, though, that the critical items list says if that's the case, it's going to result in a catastrophe, because there is no redundancy. That was the finding, as I understand it. Am I correct, Dr. Wright?
Well, that just reading the critical items list, what it says is that it's the primary O-ring which is a criticality 1, not a criticality 1R.
If you just read it in that sense, yes. But if you know how it was generated, which was that it was not redundant full time, that it was only redundant during the ignition transient, and then it was non-redundant once the joint opened up, and we knew that. We understood that, and that did enter our thinking.
In discussing this idea that the secondary seal will seat, the principle is that it's located in the correct place because of a pressure put on during making a check, which is 2 days or so before launch. After the check has been made in the VAB building, this machine is put on a carrier and carried and jiggled and so forth all the way out to the site. It stands there for 2 days and is rained upon, and we have found in other cases that water gets into the seal. Did you consider when you were discussing these, the probability or the possibility that in all this jiggling and then the water inside there freezing, making ice, that it could have displaced the secondary seal, and that your idea that the secondary seal is in exactly the right place and will seat immediately during this short transient might have even more uncertainty? Were you considering those possibilities?
Well, we were not considering the possibility of ice in the joint. We did not discuss the potential for how much the O-ring might move as a point of rolling it out, although I think the feeling is that that's a pretty stiff joint. It doesn't see any real movement, but we did not consider the possibility of ice in the joint.
Mr. Armstrong?
Approaches to performance expansions, envelope expansions in the case of airplanes, or component performance envelope expansions, normally take the position, well, I've flown in these places, and based on that and my analysis of the results of those flights, I would be willing to go this much farther for the next case. But yet your engineering group said they wouldn't be willing to go outside their existing experience race, or recommended that they not originally, and later you said, well, we'll go this much more. Was there, before the fact, any evidence or any attempt, let's say, to provide a level of expansion which the company could stand behind?
Well, there was work underway to get a better understanding of overall performance of that joint, effective rotation and effective temperature. That was the program that was kicked off after the August meeting at headquarters, where all of the joint designs and performance was reviewed. Then there was a program plan put together to look at ways to improve the performance and to get a more fuller understanding. That was underway, but we didn't have the data.
The reasons that they didn't exist after you'd flown, as you say, 144 joints or whatever, could you attribute that to some reason? Was it that you weren't interested, or didn't think it was important, or that you didn't have the resources, or how would you characterize the fact that you were only as far along as you were?
Well, it spans a fairly long period of time, but there had been a fairly long period where we had made some improvements in the layup of the putty. We'd put some controls on the time it could be exposed and that sort of thing. We tried to make some changes that were not at risk of going the wrong direction, but we had high confidence we're going in the right direction. And we're having a long period of not having any erosion or blow-by. In spite of that, in the middle of that period, in the August time period, we still concluded that we needed to proceed with an aggressive effort. So there was
I'd say a little pull and tug there in that at that time the performance was running pretty well, but at the same time the analysis said we needed to get on with some improvements, and we were searching for improvements that we could prove out without running any risks on the flight.
Mr. McDonald stated that he did feel some pressure in this meeting, and would you characterize your own feelings about pressure that may have influenced the decision process in any way?
Well, I've thought a lot about that, and there was some pressure, but I believe it's in the range of what we have normally encounter. There's whenever we're taking a position, NASA tests us on that position to explain it, justify it, that sort of thing. And that's the way I perceived we were being tested. Just how supportive, how well can we justify our position. And so we responded in that fashion. Now, I can say, I guess, that I get pressures in a lot of cases for a lot of decisions, not just from NASA, but from any people I deal with, my boss and so forth. And I think that I'm able to treat that properly and make a sound decision independent of that.
Well, let me be more specific to follow up. Do you think schedule pressure or cost pressure had significant influences in this instance?
Cost pressure definitely had no bearing on it. From a schedule standpoint, we take a lot of pride in the fact that we supported all of the launches to date, and if there was any pressure, we wanted to continue to do the job we had been doing, and that kind of situation exists every time. We have to say, are we ready to fly or are we not? And we want to be ready to fly, but we want to make sure it's safe.
Anybody get in touch with you? Any calls of any kind urging you to go ahead with this launch?
No, sir.
As far as you know, were any such calls made to anybody in Thiaco?
To the best of my knowledge, there were none. The only conversations we had were the ones on the net that have already been reported.
Just one other question. Did you realize, and particularly in view of Mr. Hardy's point that they wouldn't launch unless you agreed, you fully realized that in effect you were making the decision to launch, you and your colleague?
Yes, sir.
I had two other brief questions. Just like to return to your analysis of the data during your half an hour caucus in regard to the imprecision or uncertainty of the data. Is it not the case that the largest amount of blow-by was associated with the coldest launch, and that point was made by some of the engineers in the discussion? Why did you not consider that conclusive?
Well, we did consider, but we didn't consider conclusive simply because we'd had blow-by at the warmer temperature and we'd have erosion at varying temperatures.
But the largest amount of blow-by was at the lowest temperature.
Right. Actually, the erosion is more of a concern than the blow-by.
In fact, let's turn to the erosion. Mr. McDonald just stated that there was a case earlier in which the primary O-ring on the motor seal was on the lowest seal was eroded, and only the secondary O-ring prevented a burn through. And since you could not really rely on the secondary O-ring for the other seals, was that not also a very significant parameter? I noticed that is not mentioned at all in your analysis of your half an hour caucus.
Well, of course, we were considering the joint seal, and as Mr. McDonald pointed out, we had concluded that the
the most likely cause of the nozzle joint problem, was the fact that we had tested at a low pressure and probably had not had a seal of the primary. We had not confirmed that seal. And we'd subsequently gone to a higher pressure, the 200 psi, to be sure that the seals were proper rather than be masked by the putty. What we found was that at the lower pressures, down to 100 psi, the putty could actually hold the pressure, and so you weren't certain that the primary was seating. So we had to go to the higher pressure, which we knew the putty would not hold, and with that we could be sure the O-ring was seating. So our feeling on the nozzle joint was that that problem had been a product of not having a proper sealing primary O-ring, and it hadn't been tested adequately because it was masked by the putty.
But was that incident discussed during this half-an-hour caucus?
It was not discussed. No, sir. We were talking about the joint. It was, of course, known by everyone that had occurred.
Can you recall any previous occasion when your at least preliminary advice to NASA had been not to launch, and they wished to go ahead with the launch?
No, sir, I do not.
Was there any comment made during these conversations that you've described with NASA that this is a very unusual situation? Did anyone, for example, say that it's odd that the shoe is on this foot?
No, not in that fashion, no. It was the situation, I felt sure, or feel sure, was clear because the conversations that had gone on and the discussions by all the people about how they felt and the data they had was all on the net, so it was understood where we were coming from.
One question. In the analysis to get ready for launch, there was this one statement that temperature concerns were maybe fuzzy because there was a blow-by or erosion at a 53-degree launch, but there was also one at 75 degrees. And I'm just wondering whether getting blow-by erosion at a very good warm temperature where everything should be working quite well, wouldn't that raise concerns that maybe the system was running quite marginally, and then maybe temperature would really put it in a submarginal condition? That's one question. The other one I have is, in this package you gave us, it looks, as you proceed through the checks of the motors, more erosion and blow-by was occurring more recently than in earlier times. And the design changes, like the reduction of the structural strength of the motors, of the cases, the increase of the thrust, was there a concern at Thiokol that perhaps as time was going on and the system was asking to perform better, that perhaps the seal was getting in more trouble? I'm just trying to understand, was there that concern, or were you becoming more relaxed?
I would say when we put it all together in August, we indicated that we had a concern and that we needed to work on an improvement. We also, in that summary, said that we felt that it was safe to continue to fly as long as we had proper conditions, that is the 200 psi leak test, proper assembly, and that sort of thing. So we endeavored to summarize where we were in that August meeting, because we looked at all three joints. We looked at the field joints, we looked at the nozzle joint, and we looked at the igniter joint. We looked at all our history, and including the history that you have here, and made our assessment and identified that we ought to proceed in an orderly fashion but aggressively to make an improvement in the joint.
Well, in the August meeting then, were there some ground rules laid down, like good inspections and other conditions to keep flying?
Yes,
And
those
where are
were
these ground rules?
identified, and those were in place.
Do we have a record of what those conditions were?
It's in the August 19 briefing that we have provided copies to the Commission on. And it's memory
Did they cover
says-
anything on temperature?
No. In fact, in the copies that we provided, we also put in a February 10th set of pages reflecting the things that had happened since. And in there we said that that's the condition that we should add.
Those are the blue pages, are they not?
Correct.
Right.
Mason, in testimony that the committee has received in executive session and also in personal notes made available, you were characterized as telling Mr. Lund in this caucus to take off his engineering hat and put on his management hat as part of that final management caucus. And in fact, in your notes here from your presentation, from your charts, you indicate that you have asked them to exercise best judgment and make management recommendation. Now, since Mr. Lund was your vice president of engineering, and since he presented the charts and the recommendations not to launch outside your experience base, that is below a temperature of 53 degrees for the O-rings, in the previous 8:45 Eastern Standard Time teleconference, what did you have in mind when you asked him to take off his engineering hat and put on his management hat?
I had in mind the fact that we had identified that we could not quantify the movement of that primary, the time for movement of the primary. We didn't have the data to do that, and therefore it was going to take a judgment rather than a precise engineering calculation in order to conclude what we needed to conclude.
What triggered the caucus that Thiokol asked for, according to testimony, was the fact that NASA had expressed surprise, concern about the impact of such a recommendation of not launching below a 53 degree Fahrenheit temperature for the O-ring, and particularly the impact on schedule. During the 30-minute caucus, was there any part of your discussion that addressed that impact on schedule and what that meant to Thiokol? Any management concern on that?
Well, when you say what triggered the caucus was not NASA's expression of concern. In fact, there's a bit of irony, but from my viewpoint, the primary trigger was Mr. McDonald's comment about the fact that the secondary was in a preferred position, and that's the point that we had not actively considered in our previous discussion.
But what's the answer to the question, though? I said we had previous testimony that's what triggered it. Regardless of what triggered it, certainly those concerns were expressed. Was there discussion in that Thiokol caucus with respect to schedule and the impact of sticking to a 53 degree Fahrenheit temperature as a launch condition and what that meant?
No, there was not.
No discussion of schedule?
No, we simply addressed the issue of flight safety.
Mr. Mason, when you spoke to Lund and told him, in effect, to take off his engineering hat and put on his management hat, wasn't that pressure on your part to a subordinate that he should change his mind?
Well, I hope not, but it could be interpreted that way.
That's all. Any other? Let's adjourn. We reconvene at 1 o'clock and 2 o'clock, excuse me. And we plan to have Mr. Boisjoly, Mr. Thompson, Mr. Lund after lunch.
I got a new volume. I'm taking notes.
Okay.
Too good to read out.
Have Mr. Boisjoly and Mr. Thompson go up, huh? Why don't you, Mr. Thompson, move a mic over so you each have a microphone. This one. Okay, the commission come to order, please.
Mr. Boisjoly, Mr. Thompson, stand up, please. Raise your right hand. You swear the testimony you give before the commission is the truth, the whole truth, and nothing but the truth, and nothing but the truth. I do.
Mr. Boisjoly, you are now presently employed by Point Cycle.
Yes, I am.
And how long have you been employed by them?
Approximately 5.5 years.
How many?
5.5 years.
And what's your present position?
I'm a senior scientist, is my title. And I'm basically a staff member to the manager of applied mechanics.
And what kind of work have you been doing for the last 5 years?
I have been involved in the joints. I have gone down to the Cape and taken a significant amount of inspections of the solid rocket boosters as they've come back from flights. I've reported on that information, and that information has been used in the flight readiness reviews for the next flights. I've also participated in some of the structural analysis. Also was one of the primary drafters of the refurbishment specification on the cases themselves, particularly in the area of the joints. I have made a videotape and have given a presentation at our plant, also at Vandenberg, in a KSD concerning the inspection characteristics of the joint surfaces themselves. I have been appointed as a member of the Special SEAL Task Force that was initiated last August, and I'm in that position currently.
You've been described in previous testimony as either the leading or a leading expert on the subject of seals and joints in the booster rocket. Can I gather Mr. Thompson works with you in this connection?
Arnie used to be my supervisor. I used to work for him approximately 2 years ago, and I went out of that capacity, like I said, about 2 years ago.
Ms. Thompson, you want to give a little background of your own experience? How long have you been with Thiokol?
Been in Thiokol 21 years.
How many? 31?
21 years.
21 years. And during that time, well, what's your present job?
I'm supervisor for structures design for rocket motor cases, metallic rocket motor cases.
Mm-hmm. How many men work for you now?
About 25 people.
And are they mostly engineers?
Yes, sir.
And have you had extensive experience in connection with the solid fuel booster rocket and the O-rings and the seals that we've been talking about?
Yes, I would say so. I've been involved for about 7 or 8 years in the CASE program. I first came into it right after the first hydroproof of the cylindrical sections.
Mr. Boisjoly, do you have engineers working for you or with you?
No, I'm strictly in a staff position at this present time.
If you want to go back a little bit, you've been doing some extra work in connection with the seals and the O-rings. You want to describe that information, please?
As a result of my involvement in hardware inspections after the vehicles had flown at Kennedy, I got involved quite heavily in some of the flight readiness reviews that presented problem areas with the seals, namely the erosion that was going on.
Want to move the microphone just a little bit closer, please? Good.
Now, I was involved in going down to the Cape and inspecting the hardware after it flew. And any of the hardware that experienced problems with the seals, namely erosion, I was also involved in the preparation and sometimes the presentations in flight readiness reviews, along with Allan McDonald.
So that you have made some of the actual inspections that we've been talking about this morning in connection with erosion and blow-bys and so forth.
I was the person that was there when SRM-15 was disassembled. I was the person that inspected those joints and reported on those joints, took the samples of the blackened grease, characterized the degrees of arc that the blackened grease existed, directed the photographs taken of the joint, took the samples for chemical analysis back to Morton Thiokol for analysis of what the blackened condition actually was, and then prepared the presentations to give to Marshall on the condition of those joints.
So you had as much first-hand experience as probably anybody else in the field.
That's correct.
Perhaps you could characterize
the concern and activities that went on with respect to the joints starting back in the time before the August of '85 time period, whatever before that, where you should start.
Yeah, just along about SRM-8, thereabouts. I could be off a vehicle or two either way. We had previously to that experienced putty going around the end of the clevis and up to the primary O-ring and actually sometimes into the groove. And there was some concern expressed about that situation because the putty has a asbestos filler in it, which is a fibrous filler. And the concern was that the fibers might interfere with the sealing capability of the O-rings. Therefore, a change was made to lay up the putty in a little bit different character on the end of the clevis leg, such that when you mated, you would not see that characteristic amount of putty down there next to the O-ring. And by observation, that intent was successful because from that time on, I never saw putty pass the chamfer on the end of the clevis leg and never around the corner on the radial surface and down towards the seal. Then we would report on the erosion characteristics on the seals as we observed them. Like I said, we photographed them. We documented the degree of arc of any of the damage, both heat affected and erosion. The erosion generally is a very localized removal of the material in the O-rings, and it goes some distance longitudinally, as the charts explain that you have. And we would report on that, and that became a focal point for discussion as a problem area for the next flight readiness review. So basically, that was my task at that time.
Was there an increase in concern in mid-'85 as a result of the observations that you and others had made?
Yes, SRM-15 actually increased that concern because that was the first time we had actually penetrated a primary O-ring on a field joint with hot gas. And we had a witness of that event because the grease between the O-rings was blackened just like coal for those arc lengths that were described in the charts. And that was so much more significant than had ever been seen before on any blow-by, on any joint.
When was that flight?
That was a year ago, last January. And the reason it was so vivid in my mind is because I was at the Cape prior to the launch, giving the presentation to approximately 130 people at the launch facility on the inspection techniques on the joint to be used to ensure that any defects which had been removed from the joint were removed in a manner such that the transition on the defect was very smooth, so that the elastomeric condition of the O-ring could actually get into those imperfections because it had been smoothed out. And being an elastomer, it would do just that. And I remember watching the launch. In the launch, I went out of the VAB, and it was a afternoon launch. My recollection is sometime between 1 and 2 o'clock in the afternoon, I'm not sure. But it was reasonably cool, but yet I went out without a suit coat. During the presentation of that vehicle, after it was inspected, it was calculated by the folks back at the plant, heat transfer folks, that the seal temperature would have been approximately 53 degrees for that launch. And that was part of the characterization of the presentation in the Flight Readiness Review for the next vehicle. Now, that presentation was a very pointed discussion, a very detailed discussion, and quite frankly, I commented to Allan McDonald once or twice that had I not been personally there and been personally witnessing what I had seen and presenting what I had physically seen, I don't think we could have been able to convince NASA to continue to fly. I felt very strong about that fact because I spoke from conviction and I was challenged by just about everybody in the room about what I had reported. And I was very grateful that I was there and was able to stick by my convictions because I had seen the condition of the joint.
Mr. Boisjoly, on 51C, you saw a very blackened joint.
Yes, two of them.
However, on 61A, the temperature was 75 degrees, and that has been used to minimize the effects on 51C, saying that it occurs at warm temperature also. Would you explain the difference that you saw or heard of between the two joints?
Yeah, the difference, the SRM-22 that was used as a comparison basis was not one that I saw personally, but a junior engineer, or a younger, I shouldn't say junior, but a younger engineer who works for Arnie had actually been at the Cape and seen those joints. I questioned him and asked him to tell me in his words what he saw. What he told me was that he saw light grayish to dark grayish splotches that occurred over an arc length of approximately 40 degrees. Then we discussed the photos. He had a photo of that joint and I had a photo package of the SRM-15, and we put the photos side by side, and you could see that the SRM-15 joint had coal black color where we had photographed it, and the joint was as he described. It was not coal black. It was significantly lighter and a little bit splotchy. The splotchiness wasn't so definitive, but that's how he defined it to me. Now, on that basis, I concluded, and so presented the night before the launch, that that was extremely significant. It was very significant because it was telling us that temperature was indeed a discriminator, and that although I couldn't quantify what that discriminator was from an actual threshold standpoint, in other words, I couldn't say you can fly above this temperature, you can't fly below this temperature. I couldn't do that. I didn't know of anybody that could do that with the data we had at the time. But I was extremely concerned, and my concern ran deeper than SRM-15. It ran as a result of the SRM-16 nozzle, which the primary nozzle was compromised, and we presented that as having never sealed and as having happened in the ignition transient in launching that vehicle. Now, that was characterized as a seal that never sealed because it either was not properly leak checked because of what was explained before. I shouldn't say not properly leak checked, but it was leak checked at 100 psi, which we knew we had data that said that putty could mask a leak check at that level. We also postulated that maybe there was nothing wrong with the leak check, and maybe in the transfer of the O-ring in the groove, it had simply ridden up on a piece of contamination and never did seal. But the fact was that now you introduced another phenomenon. You have impingement erosion and bypass erosion, and the O-ring material gets removed from the cross-section of the O-ring much, much faster when you have bypass erosion, or blow-by as people have been terming it. We usually use the characteristic blow-by to define gas past it, and we use the other term to indicate that we're eroding at the same time. So you can have blow-by without erosion, you can have blow-by with erosion. Now, I don't remember the temperature of that particular vehicle, but that turned the gain up very, very high on the seal problem, extremely high. In my mind, we were, just playing with a dangerous situation. So You've seen the packages that I've turned in, and you've probably read the memo that I wrote and expressed the concern I had to make absolutely sure in everybody's mind that management was aware of my concerns, seeing that I was one of the fellows that was most involved with that particular situation.
Since you're on the task force,
yes.
Tell us the history of the establishment of that task force and what they were charged to do.
We were charged to look at alternate designs in the joint upstream of the O-rings themselves, and to also look at the seal design as it relates to the secondary seal. And that was to try to come up with something that would replace the putty, would be of a vented design, and assure that we got gas pressurization to the seal, the primary seal. Also look at an alternative secondary seal design, which would indeed follow the gap opening of the metal parts, such that should a primary O-ring be compromised in any manner, that the secondary seal would be in a position, because it was in contact with both sides of the metal parts, to be pressurized, pressure actuated, and cause the seal to be affected. And that was the primary task of this team.
To what extent were temperature considerations involved in the work of that?
To the extent that we had run tests, or Arnie actually had them run at the lab, but I was aware of them. We had run tests on O-ring resiliency. And from the team standpoint, we ceased to talk about an O-ring and started to talk about seal, because some of the seals under investigation are not O-rings. They are cross-sections that have metallic leaf springs in them, such that you will get a mechanical assist to force the elastomer to remain in contact, such that if you did violate a primary seal, you would be capable of pressurization. So with that information, we were looking at the whole regime. We were trying to get resiliency data run at the plant since last October, which I mentioned in my statement, and also that night mentioned over the phone. And we had trouble because we kept having machine breakdowns, we kept having priority problems, and here we were, 3 months later, and we still didn't have the data necessary to us to pursue it even further. So that night, we presented the information on the basis of what we knew. And what we knew, and I feel very strong about it, is that we had a problem with temperature, and it was away from the direction of goodness, and that's my phrase, because I can't quantify it, but I always use that. It's away from the direction of goodness. And we had run tests to show that the seal never lifted off in a resiliency test at 100 degrees Fahrenheit. We had a data point that night that showed that the seal lifted off in the ignition cycle for 2.5 seconds, or 2.4 seconds at room temperature, 75 degrees. We showed that it lifted off and remained lifted off for in excess of 10 minutes, because we stopped the test at 10 minutes at 50 degrees. Now, with that testing that was run initially, I, through my concern and the joints that I had witnessed, had asked them to please run one more, and that was to back off the Instron machine platens that had compressed the seal 10,000ths of an inch and see what happens. And they did that, and it remained seated. That was my comfort zone. I am the one that made the chart that Allan McDonald presented at Washington in August, which said that if you go from 0 to 170 milliseconds, you have a high probability of a good secondary seal. If you go from 170 to 330 milliseconds, you have a reduced probability of a secondary seal. And if you go beyond that point to full pressurization, you most assuredly might not have a secondary seal. Now, that was based on the information that I had at the time, and I just went in and estimated those from a pressure time trace, and made that judgment. And that was the basis of my concern, and that was also the basis of continuing to fly, because it happens, either it happens or it doesn't happen, right at the very first threshold of the ignition transient.
Thank you. Mr. Thompson, your in your group, were you or any of your people working this problem as well, or aware of this?
Yes, sir, we were, right after the January witness of SRM 15 and the disastrous effects, in my judgment, on the O-ring situation, and seeing lots of soot in both the primary O-rings of the field joints and between primary and secondary field joints and the nozzle, it appeared to me that some additional tests need to be run. And as Roger has mentioned, the resilience test was one of the first, because then if we're getting soot blow by the primary O-ring, we better be checking and making sure that our secondary is in good shape. So we devised a test to squeeze an O-ring down a nominal amount and then come off at about 4 inches per minute in an Armstrong machine. And I'd like to quantify that just a little bit, because if one looks at the rate at which these surfaces separate, it's a nonlinear function. It has kind of a toe on it at first, and then has a fairly high rate over an inflection point, and then kind of comes over the top. And if one takes a secant from time 0 to the top point, which is about 42 thousandths at 0.6 of a second, that secant was on the order of 3.2 inches per minute. And the tests that we had run up to this point, including the night that we were discussing this, was 2 inches per minute. And additionally, the concern is if one looks at the steeper slope after you come off the toe through the inflection point, that slope is on the order of 10 inches per minute. So what it means to me, and I hope to others, is that it's a very, very high rate shortly after that comes off on the order of 100 to 200 milliseconds. So the message, I believe, and I tried to convey, was that for 100 milliseconds to 200 milliseconds, Rogers indicated 170, you really probably do have a pretty good chance for a seal. Thereafter, you do not. And so to further answer the question, and hope I'm not too long, is that blow-by, of course, was an issue. And so I set up a series of tests to try and determine the factors that affect blow-by, such as squeeze, such as temperature, and in fact attempt to measure the blow-by using argon at first, and then subsequently we've changed to freon because it's a better witness.
A question about these tests to measure the rate of gap opening, if that's the proper term. Was this on an actual set of hardware, or was it a test vehicle, and how would tolerances influence that? Couldn't you get quite a varied answer depending on whether you had a tight joint or whether you had a system that was close to the other end of the tolerance?
Yes, sir. What we did, recognizing this, is first of all, it was a bench test. It was a 3-inch piece of O-ring, in fact, 2-inch piece of O-ring that was squeezed to about a nominal squeeze, which is like 40 thousandths. Many of our joints have about that squeeze. The particular one in question in the incident was 35 thousandths, 37 thousandths. And so we just merely would give it the squeeze and then back off at the simulated rate that we could do on the Armstrong machine.
Well, do you get a very results on actual flight hardware then, depending on the various production runs on the cases?
Yes, sir, we do. In fact, if you have additional squeeze, you not only have the two surfaces, the one surface pushing off, but if it's a lot of squeeze in a small O-ring groove, the side surface of the O-ring probably can always help, can also help, and that gives you additional energy to help it respond.
Well, what about the other direction, where the tolerances are on the other side?
We investigated tolerances and gaps, and we have set up a matrix that, to do that very thing. This was kind of a preliminary test we had run, and as Roger mentioned, we have refined the test and have some results now, but after the fact. And the test included squeeze, included temperature, And it also, the variable rate that we think we really have in the motor, we have simulated that by using a function generator as an input to the Instron machine so that we could generate the actual motion as we saw it.
But with the fact that the testing is somewhat late, and then that there's a lot of variables, and there's been a lot of commentary on temperature, couldn't you come up with a situation where temperature and tolerances could develop a sub-marginal joint, and that of the 144 cases that have been fired, you could run the gamut from having very good ones to very bad ones?
Yes, sir, we could. We ran, as I say, just a preliminary run that showed that it was a problem.
But would all of the parties be aware that you could have wild variations, and couldn't this develop quite a concern on everybody's part that the system was pretty tender?
My feeling the system was tender, and this was the reason I objected tonight.
That was the point we tried to make that night, is because we didn't have sufficient data.
Well, my question gets around to why wouldn't everybody have that feeling that the situation was very tender, and why wouldn't everybody develop a feeling of great concern, and then by that means develop a very, very conservative attitude towards approaching a launch?
That's what we thought happened when the original conclusions and recommendations were made, because they were quite consistent with what we had presented prior to the meeting and prior to making the charts.
I'd like to come to the night of the launch and the launch itself, or the decisions, a little while, but I'd like to go back just a minute to some of the background before we get to that point to show your concern as expressed to management. I have here a letter which appears to be one signed by you, dated July 31st, 1985, and I'll ask Dr. Keel to give it to you. And I gather from the files that we received from you, you wrote a series of letters or memos to, I guess memos is a better way to describe it.
Those were activity reports.
Yes. Expressing your concern about this problem of the seals and the O-rings and so forth. I would ask you, if you don't mind, to read that memorandum dated July 31st, which you wrote to R.K. Lund, who was Vice President of Engineering.
Yes.
Would you mind?
Yes. This letter is written to ensure that management is fully aware of the seriousness of the current O-ring erosion problem in the SRM joints from an engineering standpoint. The mistakenly accepted position on the joint problem was to fly without fear of failure and to run a series of design evaluations which would ultimately lead to a solution, or at least a significant reduction of the erosion problem. This position is now drastically changed as a result of the SRM 16A nozzle joint erosion, which eroded a secondary O-ring with the primary O-ring never sealing. If the same scenario should occur in a field joint, parentheses, and it could, then, close parentheses, then it is a jump ball as to the success or failure of the joint, because the secondary O-ring cannot respond to the clevis opening rate and may not be capable of pressurization. The result would be a catastrophe of the highest order, loss of human life. An unofficial team, parentheses, a memo defining the team and its purpose was never published, close parentheses, with leader was formed on 19 July 1985 and was tasked with solving the problem for both the short and the long term. This unofficial team is essentially non-existent at this time. In my opinion, the team must be officially given the responsibility and the authority to execute the work that needs to be done on a non-interference basis, parentheses, full-time assignment until completed, close parentheses. It is my honest and very real fear that if we do not take immediate action to dedicate a team to solve the problem, with the field joint having the #1 priority, then we stand in jeopardy of losing a flight along with all the launch pad facilities. Then I signed it and the manager that I work for countersigned it as concurred.
Thank you. I assume, Mr. Thompson, you agree with the contents of that memorandum?
Absolutely. Yes, sir.
Unless the Commission has any further questions, I'd like now to go to the January 27th and January 28th to ask you, Mr. Boisjoly, to describe in your own words your first involvement in those discussions and what was said, who took part, and your position, and later on your position.
Okay. My first
But I say you also, just before you start, sorry to interrupt, but you did make notes on the 27th about the events of that time?
Yes, I did. I made them after the meeting.
You made them after, but on the same day?
Yes, and then I made a few more notes on the day of the launch.
And you have,
prior to the launch, and then I made a short entry after the launch.
But the notes on the 27th and the 28th were made on those days?
Yes, they were.
And the last one was made after the accident?
That's correct.
In your discussion, you may refer to those notes, and we, if you have no objection, may make them public.
I kind of just paraphrased them and made them on 3x5 cards.
Fine.
But I think they essentially have the content of what's in those notes. My first knowledge about any temperature concern on the launch was approximately 1 p.m. on the 27th of January. There was a preliminary meeting held to discuss the concern at the low temperature for resiliency, soot blow by, previous launch, and static test temperatures. And there were there were quite a few people in that meeting, most of whom were engineers, some were program management. I don't remember the names, honestly. Anyways, that meeting concluded with the tempo that there was a valid concern for temperature, low temperature. Also heard sometime afterwards that it had been cold for several days. And what really impressed me about this piece of information was that it was opposite what SRM-15 had experienced. And that concerned me because when I got off the plane a year ago last January for the SRM-15 launch, it was very cold, like 17 or 18 degrees when I got off the airplane at Orlando. The next few days, although it remained cold, it got warmer. And by launch time, like I said, it was probably in the 60s, but it did get warmer. Now, what was concerning me about this piece of information was it was the reverse. It had been cold for several days, and it was getting colder. And that's why I noted that, because that just turned the gain up on my concern, because it was away from goodness again. SRM-15 that I'm referring to was the coldest launch up to that point in time. Okay, I felt we were very successful in convincing engineering management of the problem. By now, we heard that the overnight low was predicted to be 18 degrees Fahrenheit. And again, my concern deepened because what I just spoke. It was going in the wrong direction from the past experience base. A telecon was set up with Marshall Space Flight Center and Kennedy Space Center to present data over our concern about the low temperature. Now, there had been some meetings in between, and quite frankly, I'm almost a total blank because I was down in my office. I ran a calculation that showed that the O-ring shrinkage due to low temperature in dropping from 75 degrees to 25 degrees, it was just a rough number, was 0.03 of an inch. And that was due to both the shrinkage on the diameter and the effective temperature stretching it around its circumference and thus causing the diameter to shrink down again. There was roughly a 50-50 split in those numbers. But the bottom line was it was about 0.03 of an inch. Okay, that shows me that squeeze wasn't really in effect. Squeeze was not an issue. It never has been an issue with me because if you look at all the eroded O-rings, they don't correlate with squeeze. The O-rings that you would expect to be eroded are those that have the lowest squeeze, and that's not the case. So squeeze was never an issue, but I ran the number anyways to assure myself that it was okay, which it was. Okay, the telecon data, and I must emphasize this, we had very little time to prepare data for that telecon. when it was decided in a group in our conference room that we would take a systematic approach and assign certain individuals certain tasks to prepare, we all scurried to our individual locations and prepared that information on a timely manner. That's why the charts, for the most part, are hand-printed or handwritten, because we didn't have time to get them even typed. Each person during the telecon presented their own charts. Just for the record, I presented charts 2-1, 2-2, 2-3, and I also presented 3-1, which I did not prepare, but which was sequenced right after the one that I did, and I was asked just to present it, which I did. I presented 4-1 and 5-1. I expressed deep concern about launching at low temperature. I presented chart 2-1 with emphasis. Now, 2-1, if you want to see it, I have it, but basically that was the chart that summarized the primary concerns. And that was the chart that I pulled right out of the Washington presentation without changing one word of it, because it was still applicable. And it addresses the highest concern of the seal joint in both the ignition transient condition and the steady state condition. And it really sets down the rationale for why we were continuing to fly. Basically, if erosion penetrates the primary O-ring seal, it's a high probability of no secondary seal capability in the steady state condition. And I had two sub-bullets under that, which stated, bench testing showed O-ring not capable of maintaining contact with metal parts gap opening rate to maximum operating pressure. I had another bullet which stated, bench testing showed capability to maintain O-ring contact during initial phase, parentheses, 0 to 170 milliseconds of transient. That was my comfort basis of continuing to fly under normal circumstances, normal being within the database we had. I emphasized when I presented that chart about the changing of the timing function of the O-ring as it attempted to seal. I was concerned that we may go from that first beginning region into that intermediate region, from 0 to 170 being the first region, and 170 to 330 being the intermediate region, where we didn't have a high probability of sealing or seating. I then presented chart 2-2 with added concerns relating to the timing function. And basically on that chart, I started off talking about lower temperature than current database results in changing the primary O-ring sealing timing function. And I discussed the SRM-15 observations, namely the 15A motor had 80 degrees arc of black grease between the O-rings. And make no mistake about it, when I say black, I mean black, just like coal. It was jet black. And SRM-15B had 110 degrees arc of black grease between the O-rings. We would have low O-ring squeeze due to low temperature, which I had calculated earlier in the day. We would have higher O-ring shore hardness. And that is the characteristic similar to the hardness test that's done on metal, except that it has a different anvil size. And when you press against the elastomeric material, that is the measure of how far a standard size anvil will go in to the particular elastomer, and it gives you a measure of relative hardness of the substance. Now that would be harder. And what that really means, basically, is that the harder the material is, it would be likened to trying to shove a brick into a crack versus a sponge. That's a good analogy for purposes of this discussion. I also mentioned that thicker grease, as a result of lower temperatures, would have a higher viscosity. It wouldn't be as slick and slippery as it would be at room temperature, so it would be a little bit more difficult to move across it. We would have higher O-ring pressure actuation time, in my opinion, and that's what I presented. If action time, and these are the two, these are the sum and substance of what I just presented. If action time increases, then the threshold of secondary seal pressurization capability is approached. That was my fear. If the threshold is reached, then secondary seal may not be capable of being pressurized. And that was the bottom line of everything that had been presented up to that point.
Did anybody take issue with you?
Not, well, yeah, I'm coming to that. I also showed a chart of the joint with an exaggerated cross-section to show the seal lifted off, which has been shown to everybody. I was asked, at that point in time, I was asked to quantify my concerns. And I said I couldn't. I couldn't quantify it. I had no data to quantify it, but I did say I knew that it was away from goodness in the current database. Someone on the net commented that we had soot blow by on SRM-22, which was launched at 75 degrees. I don't remember who made the comment, but that's where the first comment came in about the disparity between my conclusion and the observed data, because SRM-22 had blow by at essentially a room temperature launch. I then said that SRM-15 had much more blow by indication, and that it was indeed telling us that lower temperature was a factor. This was supported by inspection of flown hardware by myself. I was asked again for data to support my claim, and I said I have none other than what is being presented, and I had been trying to get resiliency data, Arnie and I both, since last October, and that statement was mentioned on the net. Others in the room presented their charts, and the main telecon session concluded with Bob Lund, who was our Vice President of Engineering, presenting his conclusions and recommendations charts, which were based on our data input up to that point. Listeners on the telecon were not pleased with the conclusions and the recommendations.
What was the conclusion?
The conclusions were that we should not fly outside of our database, which was 53 degrees. Those were the conclusions. And we were quite pleased because we knew in advance, having participated in the preparation, what the conclusions were, and we felt very comfortable with that.
Said of that conclusion?
Mr. Bob Lund.
Right.
He had prepared those charts. He had input from other people, but he had actually physically prepared the charts, and he prepared them. It was about that time that Mr. Hardy from Marshall was asked what he thought about the MTI recommendation. And he said he was appalled at the MTI decision. Mr. Hardy was also asked about launching, and he said no, not if the contractor recommended not launching. He would not go against the contractor and launch. There was a short discussion that ensued about temperature not being a discriminator between SRM-15 and 22. And shortly after, I believe it was Mr. Kilminster asked if he would, excuse me, I'm getting confused here. Mr. Kilminster was asked by NASA if he would launch, and he said no, because the engineering recommendation was not to launch. Then MTI management then asked for a 5-minute caucus. I'm not sure exactly who asked for that, but it was asked in such a manner that I remember it was asked for a 5-minute caucus, which we put on the line on mute and went offline with the rest of the net.
At the time that you made the recommendation, last I called made the recommendation not to launch, was that unanimous recommendation as far as you knew?
Yes, I've got to make something clear. I have been distressed by the things that have been appearing in the paper and things that have been said in general, and there was never one positive pro-launch statement ever made by anybody.
Thank you.
There have been some feelings since then that folks have expressed that they would support the decision, but there was not one positive statement for launch ever made in that room. Yeah. Picking up where the caucus started.
Just to give you, is that your recollection too, Mr. Thompson?
Yes, particularly in the caucus. I think Roger and I were the only people that expressed our views.
But no, you should proceed with the launch at that time.
Not amongst the people that I was able to hear.
Hey, you said there was some confusion in your mind as to Mr. McDonald's position at that time. He came on with a comment about the secondary ring seating, that you should consider that.
That's correct. When Al first came on the line and explained the situation about the primary and secondary O-ring and how the secondary O-ring was in position, I had a flash of confusion in my mind as to what he was saying. But I, having worked on the SRM-15 presentation and the SRM-16 presentation, realized exactly what he was trying to say, but I did have that tinge at the beginning. So there was definite misunderstanding about Al's statement. There's no question in my mind, because I had it, and I was probably closer to that joint than most anybody else. And I had that tinge, and I so stated that to you. Okay, the caucus was started by Mr. Mason stating that a management decision was necessary. Those of us who are opposed to the launch continue to speak out, and I'm specifically speaking of Mr. Thompson and myself, because to my recollection, he and I were the only ones that vigorously continued to oppose the launch. And we were attempting to go back and re-review and try to make clear what we were trying to get across, and we couldn't understand why it was going to be reversed. So we spoke out and tried to explain once again the effects of low temperature. Arnie actually got up from his position, which was down the table, walked up the table, put a quad pad down in front of the table, in front of the management folks, and tried to sketch out once again what his concern was with the joint. And when he realized he wasn't getting through, he just stopped. I tried one more time with the photos. I grabbed the photos and I went up and discussed the photos once again and tried to make the point that it was my opinion from actual observations that temperature was indeed a discriminator, and we should not ignore the physical evidence that we had observed. And again, I brought up the point that SRM-15 had a 110-degree arc of black grease, while SRM-22 had a relatively different amount, which was less and wasn't quite as black. I also stopped when it was apparent that I couldn't get anybody to listen.
At this point, did anyone else speak up in favor of the launch, or?
No, sir. No, sir. No one said anything. To my recollection, nobody said a word. It was then being discussed amongst the management folks. After Arnie and I had our last say, Mr. Mason said, "We have to make a management decision." He turned to Bob Lund and asked him to take off his engineering hat and put on his management hat. From this point on, management formulated the points to base their decision on. There was never one comment in favor, as I've said, of launching by any engineer or other non-management person in the room before or after the caucus. I was not even asked to participate in giving any input to the final decision charts. Went back on the net with the final chart, which was the rationale for launching, and that was presented by Mr. Kilminster. It was a handwritten on a notepad, and he read from that notepad. I did not agree with some of the statements that were being made to support the decision. I was never asked nor polled, and it was clearly a management decision from that point. I must emphasize, I had my say, and I never take any management right to take the input of an engineer and then make a decision based on that input. And I truly believe that. I've worked at a lot of companies, and that's been done from time to time, and I truly believe that. So there was no point in me doing anything any further than I had already attempted to do. I did not see the final version of the chart until the next day. I just heard it read. I left the room feeling badly defeated, but I felt I really did all I could to stop the launch. I felt, personally, that management was under a lot of pressure to launch, and that they made a very tough decision, but I didn't agree with it. One of my colleagues that was in the meeting summed it up best. This was a meeting where the determination was to launch, and it was up to us to prove beyond a shadow of a doubt that it was not safe to do so. This is in total reverse to what the position usually is in a pre-flight conversation or flight readiness review. It's usually exactly opposite that.
Do you know the source of the pressure on management that you alluded to?
Well, the comments made over the net is what I felt. I can't speak for them, but I felt it. I felt the tone of the meeting exactly as I summed up, that we were being put in a position to prove that we should not launch, rather than be put in the position and prove that we had enough data to launch. And I felt that very real.
These were the comments from the NASA people at Marshall and at KSC.
Yes.
I think you were trying to prove the seal would fail.
That's right.
And of course you couldn't, because as a matter of fact it didn't. That is, 5 of them didn't, and only 1 of them did. And therefore,
right.
Had you proven that they would fail, you would have found yourself incorrect and under criticism, because 5 of them didn't fail.
That's right. I was very, very concerned that the cold temperatures would change that timing and put us in another regime. And that was the whole basis of my fighting that night. That's right.
To a point that they were intolerable.
That's right.
Mr. Boisjoly, your correspondence in the summer of '85 indicates that the heightened sensitivity of the O-ring problem at Thiokol was really initiated by heightened sensitivity about it at NASA. And, for example, references made to the problem that has escalated so badly in the eyes of everyone, especially our customer, NASA. Now, was any mention made during the telecon net with NASA the evening of January 27th of the how the NASA view had moved from this heightened sensitivity to the O-ring problem to the position that they were now putting forward at the January 27 telecon?
No, that wasn't mentioned, but in fact they were just as concerned as our counterparts that we worked with, that they were right on top of this SEAL task force team with us, and we had status reviews going on all the time. In fact, anytime we'd hit a situation where they felt we weren't going quick enough, we ended up having a visit, and they would just be there and watch over our shoulders and make darn sure that we were proceeding in a timely manner. So that, to me, told me that they were just as concerned about it as we were.
Mr. Boisjoly, could you tell me something more about the
team that was set up? You alluded to it in your letter of 31 July, and you asked that team be reconstituted and made more urgent. Did that happen?
In a way.
Who was on that team?
Don Kettner headed the team up. I was a member. Brian Russell was a member.
Were the NASA members?
Oh, they had a counterpart team, yes. They had members of their team. Our main interface was with a gentleman called Jerry Peoples and Ron McIntosh. But they had their folks involved also. They had a similar...
You had meetings with representatives from both
yes, we did.
NASA and Thiokol.
Yes, we did. When we outlined a plan on how we were going to proceed to fix this problem, they were part and parcel to that plan.
Now, this is the team that evolved a number of solutions to this problem, some of which have already been publicized.
That is correct.
And some of those solutions were short-term solutions and others were long-term solutions.
We categorized them, at least I did in all my notes, as short-term solutions, medium-term solutions, and long-term solutions. And to give you a flavor for what put what in what category, was I considered a short-term solution, for instance, a 292 diameter O-ring, which would have afforded us 12 thousandths more squeeze and still not have an overfill condition in the groove with the elastomeric material. Also couple that with selective shimming that would make the tang and clevis more concentric to one another and take as much of the free volume gap on the outside away to make sure that we were putting more and more squeeze on the O-ring and less chance for the gap to open up to the rate that it's opening.
Do you have some estimate of how long the short-term solutions would have taken?
Yeah, we had assembly tested a 292 O-ring in a QM in some static motor joints, some inert motor joints, put them together and found that we had good success with that. They are currently installed in the aft two field joints of the QM5 test motor that was ready to fire about 2 weeks ago at our plant. So we had made that progress, and we were well on our way to showing that those seals were working the joint. Now, I must emphasize that the QM5 motor is a film-along case motor, and it is a joint with a capture feature on it that doesn't have the gap opening. But the major issue on a 292 O-ring was the assembly characteristics of it, and we were getting like 12 thousandths of an inch squeeze for free. Basically, that was the short-term issue that we could implement as quick as possible.
Did the team report on a regular basis to both NASA and fire call management?
We had status report with the Marshall folks at regular intervals, and we had a Friday teleconference at midday and status the proceedings of that previous week with them.
So everyone in the telecon on January 27th was aware of the work of this team, the solutions that it proposed. And
I don't know that everyone was, but there were a number of people that were. Yes, I don't know. I cannot make this statement that everybody that was on the telecon knew about that. For instance, I had never heard Cecil Houston's name before. I didn't know that he was a Marshall type until I heard on the telecon afterwards that he was down at KSC. I had not met that gentleman, so I don't know if he knew it or not. And I don't know if some of the other folks knew, but there were enough folks on that telecon that knew what the status was.
What about Mr. Malloy and Mr. Hardy? Do you know if they knew?
I don't have sure knowledge of that. No, I don't know.
I want to get away for a moment from the temperature question, which comes up later, and go back to the earlier time when you're worrying about these things. And I would like to know whether already you felt that there was a serious problem in flying, even at 53 degrees, for the following logic is possible, perhaps, and you'd correct me. If the primary ring were to start to erode and were to take enough time to erode that it takes, the pressure builds up to 600 psi or so, then if there's joint rotation from the result of that, the secondary seal may fail if the erosion would get all the way through the primary seal. The erosion got through a third of the way of the primary seal, in fact, in 15C.
Now,
do you feel that you understand the process of erosion well enough to know that it was unlikely to go 3 times as far?
Yeah, I think we need to clarify one thing. 1/3 of the seal was not eroded. 1/3 of the allowable erosion number occurred. And you really have to clarify that, because we're talking about a seal diameter that's 280 in diameter. Okay? And we really eroded about 32 thousandths of an inch on SRM-15. And the factor of 3 is being used against subscale data, which showed that we were able to seal an eroded seal on a subscale rig that had 10-inch diameter seals that up to 1/8 of an inch. Then we had a window where we failed to seal, and then we had another one up to, I believe it was 145 or 147 thousandths of an inch that also sealed. Now, the analysis from a gas dynamics standpoint, which is out of my area, had been conducted, and they found an excellent math model of that erosion process. And it correlated extremely well with this subscale test data, which had been run about a year before. And there were 27 tests that would characterize that erosion. They ran most of them at 3 seconds, and then my recollection is there was 1 or 2 5-second tests and 1 or 2 20-some-odd second tests to show that it was indeed an ignition transient. And what that test was all about was they had a metal orifice, was a rectangular orifice. It was 40 thousandths wide and had different characteristic heights. And they ran a parametric study using that test rig, and determined what the erosion rate, or not the rate, but the erosion depth was as a function of the orifice size. Then the math model was made and characterized that, and my recollection is they were within 12% of all the test data, and they were very pleased at the characterization analytically of what was going on. So from an erosion standpoint, I think it is fair to say that there was indeed sufficient margin. But that was not the issue. Erosion was not the issue. What was the issue is, can you stand a longer period of time in an attempt to seal before the erosion eats you alive and you don't have a seal period? Because once you get flow, you have two types of erosions. You have blow-by erosion and impingement erosion. The 27 tests characterized impingement erosion only. There were no blow-bys in that end. And I might say, too, we ran tests on that same rig without an orifice and pressurized it exactly the same way on an unprotected O-ring, and there was not even a sheen missing on the O-ring. So the analysis characterized that very well, and they understood it very well. What it is it's a volume filling problem as a function of time. The higher the volume, the more the time the hot gas flows if you have a blow-by through the putty. That will enable you to get erosion. And I felt very confident they had a good analytical handle on that.
Thank you. I have another question on the other side now, which is the blow-by early on, that is in the first, whatever you call it, 170 milliseconds.
Yes.
During which it was supposed that the secondary ring would be close enough to the right place to be sealed.
Yes.
But now I'm going to talk about the lower temperature. Under those circumstances, where the thing is standing around and has no resilience, and in fact when the engine goes off, it swings or twangs back and forth, and there are various stresses that have been there since the time that the ring has been pushed into place by the test, which I now discover was 28 days earlier, not just 3 days earlier.
Right.
Isn't it possible that the secondary ring has gotten squeezed to smaller size than it should be, and then when it bends back, it leaves a hole, that there's no 170 milliseconds at all, that it's already too small because it has so low resilience time. It takes so long for it to respond after it's been squeezed.
That is possible. I had done a series of tests relating clevis opening problems back about 3 years ago, where we had experienced a phenomenon where the clevis was opening up, maybe 3 to 5 thousandths of an inch over its original manufactured dimensions. And we tried to run that down and pin that down as to where that came from. In the attempt to do that, I ran a series of tests which took an empty cylinder segment, and I actually characterized when it was round what happened to the clevis. When I ovalized the case, what happened to the clevis. When I took the case and put shims underneath the longitudinal direction, what happened to the clevis. And characteristically, with very large numbers, like when I ovalized it to a value of approximately an inch, I could only affect the clevis gap opening, say, several thousandths of an inch. And so, even though you get motion, it was not characterized as a major motion relative to the squeeze that we had. But in reference to temperature, which is what you're talking about, yes, you could very well have had that situation.
Boisjoly, we've had some data on, we've had some data, you probably know, on experience with water accumulating in the field joint while it's standing out there on the stack. As Dr. Feynman pointed out, 51L stood out there for 28 days, during which there were some heavy rainstorms, wind-driven rain. What would the effect, and then we also had cold temperatures the night before and a couple of nights earlier. What would be the effect if water accumulated in the field joint and then froze during these hard freezes?
Well, first of all, I had no prior pre-launch knowledge of that occurring. I had since found out that there was a vehicle that they changed out one of the segments, and when they pulled the pin, water poured out of the joint. Did not know that prior to the launch. we have been looking at that since the incident and actually have run a test, and the effect on the actual opening of the clevis, the actually spreading of the clevis itself, was almost non-measurable. And we attribute that, I guess, to the fact that you cannot fill the joint by configuration all the way up to the secondary O-ring. Now, if you postulate that there was enough grease in there and you actually moved the grease with the ice, then you could move the O-ring, but that's speculation at this point. It looks from the design configuration of the joint that if you fill the joint with water, you'd still have an air column that would probably be on the order of 5/8 to 7/10 of an inch high, and you would simply compress the air column, and it appeared like you wouldn't be able to generate enough pressure to transfer the ring. But in all fairness, we're running tests to find that out. We haven't completed them yet. I should say Marshall.
Mr. Boisjoly?
Yes.
Were you at Firestone? The design of the joint for these SRMs was developed?
No, I was not.
But you were there when SRM-8 was fired, were you not?
Yes, I was there when SRM-1 was fired.
Can you account for what appears to be a concentration of erosion and blow-by cases in these O-rings following SRM-8 as opposed to prior to SRM-8?
That had been a topic of much discussion over the years, and there was a putty change. The original putty was a Randolph putty, and then they simply stopped making it. No, excuse me, not Randolph, Fuller O'Brien, excuse me. And they simply stopped making it. And then we switched to a Randolph putty, and that is a simultaneous general area of time sequence with the change in the layup of the putty to bring it back around from the edge of the clevis so that we were sure there wasn't any putty down by the O-ring. But that hasn't fully tied together either, because the first erosion that was ever indicated, to my knowledge, was on SRM-2, or SPS-2, the second flight. In fact, the second flight had the most erosion of any of the O-rings in the field joint. So we've been struggling with that because the data appears just totally random. If you look at the degree locations, if you look at the temperatures, if you look at it's random in regards to erosion per se.
Recall when the critical items list was amended in December '82 to make it a Crit 1 instead of a Crit 1R?
I was at Thiocol at that time. But you know, I don't even know what a CIL is.
Oh, I see.
I'm hearing all this for the first time. I just don't know.
Thank you.
From your point of view in the engineering group, did you feel that perhaps particular constraints needed to be established on the operation of the motor in a case and its joints that hadn't been, and for example, temperature related or other function related, and was that passed up the line at all?
Yes, I did feel impressed to, back in the times of STS-1, which is structural test article, STA-1, structural test article, we discovered that the joint was opening up rather than closing, as our original analysis indicated. And in fact, it was quite a bit. It's up to, I think, 50,000, 52,000 at that time for the primary O-ring. At that point, at that same meeting, we went to Marshall, discussed the problem, and we also indicated, in fact, I think it was me, that indicated that the secondary O-ring in certain worst-on-worst conditions, pressurized, even without resilience considered, could be open, could be non-contact with the adjoining surface. And so we have been working with these problems for the last several years, and of course you can immediately see our response, both Roger and myself. We know that we need elastomeric seal very badly, more so than in many hydraulic applications, because if you look at the usual, probably a dynamic seal, but nonetheless, the requirements for a 70 durometer O-ring, 1,000 psi, people want to talk about 6,000 or 7,000. And now we're talking about that type of clearance to start with, but coupled with another 50 thousandths of motion. And so it's a elastomeric problem of the first order in my judgment. And what's required is a viscoelastic type of phenomena, and we all know that if any viscoelastic material is very temperature sensitive.
Well, did you in fact, or do you know of specific recommendations being made with respect to establishing limitations of any type on launch?
Yes, sir. Several changes were made. We looked at the O-ring tolerances. We looked at the O-ring groove tolerances. We looked at, and we decreased, and on the side of goodness, as Roger would say, all of those things. In addition to that, the shim, we would call it a centering strip at that time, was 20 thousandths. We replaced that with a M-type clip that goes over the pins in that area, and increased that to 32 thousandths. And these are some of the things we've made an attempt to make the joint better from where it was originally.
And is all the recommendations that you made, to your knowledge, were accepted and implemented?
No, sir, not all of them were made. Recently, and as late as August of '82, I wrote a memo to my management, project engineering, indicated that we should stop flying until such point as we could double the squeeze on the O-rings.
What was the date of that?
About the 22nd of August.
What year?
85.
Said 82, I think. 85.
Yes, 85, I'm sorry. And my recommendation there was to double the, I went through an example in the memo, I think it was SRM 20, where if we went to the shim that Mr. Boisjoly has indicated, a full shim, which is about a 55 thousandths shim versus a 32 thousandths shim, coupled with a 292 O-ring, which is about the largest O-ring we can get in there with confidence that we're not going to nick it when we assemble, that this would about double the squeeze on the O-ring, which we felt was an important thing to do. And I realized at that point that the O-ring committee that has been dispatched to discover these things had in fact discussed that, but it was my view that we needed to get it into the flights right away.
Were any recommendations with respect to temperature of the seal area at launch, to your knowledge?
Not at that time, but that's one of the reasons is if you get additional squeeze on it, particularly the secondary and the primary will have a better chance of seating, we think, with additional squeeze, and the secondary will get more help from the sidewalls of the O-ring groove and help its resiliency problem. And we know that additional squeeze also helps in extending the time that the O-ring is in contact with the seal.
Boisjoly mentioned the capture ring as having been included, excuse me, in one of the tests. At what point, if ever, was the capture ring seriously considered for adoption? And as I understand it, and appreciate your comment on this, the capture ring is a flange which is intended to arrest the opening up of the two seal area, the area of the two seals. But when was that first seriously considered, or has it been seriously considered for production?
When it was first brought to my attention was in the design of the filament wound case. I believe someone from Marshall suggested it in the adapters for the filament wound case, and it was roughly, I think, 2.5 or 3 years ago. And it seemed like a good idea because what it does, it holds that inside flange in against the tang, and our finite element analysis indicate that instead of opening on the order of 50 thousandths, it cuts it down to 5 or 6 thousandths, which is in the direction that we need to be going.
Is that been considered for adoption, or has it been adopted in the field?
Yes, sir. It particularly has come to recent attention because of the heads-up program where we have discussed higher pressure, going up to 1110 pressure.
Mr. Thompson, could you tell us what happened to those recommendations you made in August of 1982? 85, I beg your pardon. Were they ever implemented?
No, sir, they were not.
Do you have any idea idea why not? Or did you ever receive a reply back from management explaining what they might do?
No, sir, I did not. The person that I wrote it to, directly involved in management, has since transferred down into my group again. So that may have been part of the problem, but management was aware of it because of questions and feedback that I received from it.
But you got no formal response from management on it?
That is correct.
On the capture flange, I have a couple more questions. Some time, I take it the installation of the flange is an integral part of the case, is that correct?
Yes, sir. It's part of the tang, and as it comes in, it gauges first on a tapered basis, and then it comes into a cylindrical basis.
Please go ahead.
At first, it was attempted to have two tapers fit, but the tolerances became very unreasonable, so we would engage first on two tapered surfaces and then come into cylindrical engagement where we could maintain the same type of tolerances that we have on the sealing joint.
Does that involve, or would that involve, a change in the forging process or the manufacturing process, or the forging billet?
Yes, sir. The inside bark on the forging was not quite sufficient to every time assure that we'd be able to find the part.
Would a change of that magnitude been practical for your company to undertake without the concurrence and authorization from NASA?
No, I think that would take a high cooperation between ourselves and NASA. It is quite a large undertaking, of course.
Well, could you clarify for me if that in fact has been undertaken and what the first implementation dates were or might be? Obviously, it wasn't on 51L.
I think that it's indicated to me that on a general effort that it was on the order of 18 months, but on a basis of an extremely large effort, a wartime effort, I think was the word that was used, it could be made available in 12 to 13 months.
Well, are any under process of being manufactured at the present time with the
yes,
capture flange?
I think several forgings have been ordered, and I don't know if it's a full flight set or not. I'd have to, some other people would have to answer that, sir.
I'd like to address that. On the SEAL team, that was part of the long-term fix, and there had been some forgings ordered, and the expected delivery was in February of 1987. And that was in the works, and that was part of the peripheral action, if you will, on a long-term basis of the SEAL test team.
Have they been tested yet?
No, sir, there haven't been one delivered.
When is the test scheduled?
Well, the first delivery was scheduled for February of 1987, so you wouldn't be able to test until after the hardware was received.
I'd like to ask a question about the putty. Do you, or does anyone know what the impact of temperature is on the putty and the formation of blowholes?
We have formation of bubbles. We have, interpret the first part before you said bubbles. We have since then, during the investigation, which we of course didn't know at the time we were making this decision, have tested putty in a putty test fixture somewhat similar to what the motor has, only instead of pressurizing from the outside that we usually do in running our seal pressure test, we pressurize from the inside, and in some cases, on the worst small clearance basis, it held pressure for about 3,200 seconds.
I should amplify, the night of the launch, the only data we had in our possession on the putty was that we had run temperature tests down to 40 degrees, and that was the characterization that determined the leak check pressure to ensure that the leak check pressure was not masked by the putty. And we have held up to 100 psi with the putty pressurized through the leak check port. And so we had temperature data at 40 degrees on the putty at that particular time. And we determined that 200 psi would be a conservative number that would bracket all the testing that had been done, and we would have a leak check at 200 psi for 15 minutes with an open nitrogen gas source to ensure that the putty was not masking a leak in the O-ring, and we drop to 0, repressurize to 50 psi, and run the actual low pressure leak check on the seal. 50 psi is a very severe check on an O-ring seal at low pressure. Holding that for 10 minutes and allowing a 1 pound drop is a very, very small leak on the order of an atomic energy type reactor leak.
There's one thing that disturbs me somewhat about the qualification test in regard to the putty. So I understand that during the qualification test, the putty was actually smoothed out, or there were attempts made to eliminate any imperfections in the putty. But in fact, during an actual launch, that is not done. So in that sense, the qualification test did not truly simulate launch conditions. Did that disturb anyone?
Yes, sir, that's true. To assemble these motors under a horizontal condition, which we were doing for the development motors and the qualification motors, the motors go out of round, probably more so than they do during a normal stacking vertical operation. And so the putty is probably moved more than it would be during normal stacking. So, and probably more blowholes were generated, and you can see we sometimes call them volcanoes in the putty.
You say probably. You don't really have any data. Does anyone, or has anyone, actually photographed the condition of the putty or examine the putty when the vertical stacking is done, even early in the program? I had heard that someone was lowered in a bosun's chair during the early phases of the program to examine the putty on a field joint. Do you know whether that has ever occurred?
Yes, sir. I don't have any detailed knowledge on that. We do know that as the tang is inserted into the clevis, and once the O-ring covers up the on the tang, the sealing surface, the residual air is compressed. And we know for a fact that sometimes that air that's compressed will cause a blow-by just on tang insertion.
So I wonder if I could go back to a broader question. You talked about data that you couldn't get, resources that you didn't have. Mr. Thompson has mentioned a letter that he put in August that he got no response to. You wrote an activity report on the 4th of October that characterized some of this. Could you summarize some of the things you said in that activity report, the key points, please?
I just got to check and make sure I know which one you're speaking of.
It's titled SRM Seal Problem Task Team Status. And it starts out with the team generally has been experiencing trouble.
Oh, okay, I have it. Was written October the 4th?
Yes.
Okay. You want me to read it?
Well, the pertinent points, I'd like you to make those points, if you would.
I felt, as I stated in my original memo before the team was formed, that the only way that we could pull off a timely resolution to this problem was to have people dedicated to this problem full-time with full cooperation. And I felt that wasn't coming to pass. I felt very strongly that we were working towards a solution in a timely manner, but we were getting
Short memorandum.
Okay.
Dr. Keel will give it to you. There's a little trouble there. Yeah.
This is an activity report that I turned in. It said SRM Seal Problem Task Team Status. The team generally has been experiencing trouble from the business-as-usual attitude from supporting organizations. Part of this is due to lack of understanding of how important this task team activity is, and the rest is due to pure operating procedure inertia, which prevents timely results to a specific request. The team met with Joe Kilminster on 10/3/85 to discuss this problem. He wanted specific examples, which he was given, and he simply concluded that it was every team member's responsibility to flag problems that occurred to organizational supervision and to work to remove the roadblock by getting the required support to solve the problem. The problem was further explained to require almost full-time nursing of each task to ensure that it is taken to completion by a support group. Joe simply agreed and said we should then nurse every task we have. He plain doesn't understand that there are not enough people to do that kind of nursing of each task, but he doesn't seem to mind directing that the task nevertheless gets done. For example, the team just found out that when we submit a request to purchase an item, that it goes through approximately 6 to 8 people before a purchase order is written and the item actually ordered. The vendors we are working with on seals and spacer rings have responded to our request in a timely manner, yet we, MTI, cannot get a purchase order to them in a timely manner. Our lab has been waiting for a function generator since 9/25/85. The paperwork authorizing the purchase was finished by engineering on 9/24/85 and placed into the system. We have yet to receive the requested item. And the reason I made an issue of that is because we had heard it was on the shelf down in San Diego. It was simply a matter of picking it up and using it. This type of example is typical and results in lost resources that had been planned to do the test work for us in a timely manner. I, for one, resent working at full capacity all week long and then being required to support activity on the weekend that could have been accomplished during the week. I might add that even NASA perceives that the team is being blocked in its engineering efforts to accomplish its tasks. NASA is sending an engineering representative to stay with us starting October 14th. We feel that this is the direct result of their feeling that we, MTI, are not responding quickly enough on the seal problem. I should add that several of the team members requested that we be giving a specific manufacturing engineer, a quality engineer, a safety engineer, and 4 to 6 technicians to allow us to do our tests on a non-interference basis with the rest of the system. This request was deemed not necessary when Joe decided that the nursing of the task approach was directed. Finally, the basic problem boils down to the fact that all MTI problems have number one priority, and that upper management apparently feels that the SRM program is ours for sure and the customer be damned. And I signed it October 4, 1985.
May I turn the subject a little bit around now to another aspect of it? One of our responsibilities is to attempt to determine the cause or causes of the accident. I guess both you gentlemen have suggested in these memos that if certain things were not done, a catastrophe might result. Looking at the pictures that we now have available to us, which show a puff of black smoke during the less than the first second of the launch, which was about 25 feet high. What is your opinion? Is that consistent with the concern that you had that a catastrophe might occur in that joint?
Okay, we should back up and give you a little bit of background information first. It was everybody's considered opinion, including mine, and I'm not a solid rocket motor man. I don't know anything about the propellants or anything like that. But it was everybody's considered opinion that if we developed a problem, that we'd blow it up on the pad, and that we would never even lift off the pad. There's been a lot of speculation about the puff of smoke. It hasn't really been determined what it is, where it came from, for sure. I mean, there's a lot of speculation. But if that was a joint, then that supports the leak, seal, leak theory, which is to say that you had a puff of smoke or a puff of products of combustion past both seals at a very early stage in the ignition transient. Then you sealed with whatever remaining material you had left in the seals, and you can postulate this for either the primary or the secondary. It'll work both ways. And then at some time later, due to either going through a max Q environment or vectoring of the nozzle, that you can, and vibration or aerodynamic forces, whatever you want to characterize, that there wasn't that much left, and it spit it out at that point in time and started to leak again. That has not been really determined at this
I
point.
understand.
But that's a
I was just
characterization.
really asking whether the first puff of black smoke, which has been described as about 25 feet high, is not inconsistent with the theory that you've been concerned about.
That's right.
Mr. Mr. Thompson, do you agree with the comments that Mr. Boisjoly made earlier about the discussions in the telecom and other discussions that you engaged in?
Yes, sir. I think I'm prepared to talk about these things, but I think it's been mentioned. Most of the points that I have been brought out. So
Well, why don't you, if you'd like to, look over your notes and see if there's anything you want to add. We'd perfectly glad to have you go through the whole thing. Maybe you can glance at them and see if you want to add
I can
anything.
just quickly summarize, if that's
Sure,
okay.
why don't you do that?
About 10 o'clock in the morning of January 27th, I received a phone call from Mr. Boyd Brenton. He's project manager, project engineering. He called me from Marshall and told me about the 18-degree temperature that was indicated that night. And this particular phone call was prompted by Mr. Larry Ware of MSFC, program manager, and indicating that they were both concerned about this, and they asked me how I felt and if I felt concerned, and of course I told them that I did. And it went through a series of meetings up through engineering throughout the day, ending up finally in Mr. Lund's office, and we had concluded there that we would not launch if the temperature were anything lower than 53 degrees. So at this point I felt fairly content, and we met back over in the engineering conference room, we call the MEC room, and prepared to make charts, and you've heard much of this conversation. And I guess the only thing I'd like to add to it is I also heard that Marshall's reaction is that they were appalled at our recommendation, and I was very much surprised by this, having had the experiences over the years and how careful and conservative these people are, and I really admire them. So I was extremely surprised and really not ready for this type of a recommendation. And so I guess we had put together some things. Probably we may have put together some more if they had any anticipation that this were not going to be received. But I think we pretty well got everything out on the table that we had in mind. And they indicated that the seal was not a function of temperature. And being a viscoelastic seal, it had to be a function of temperature in my thinking. And although I was not unable to explain the SRM-22, where we got some soot there also, and a supposedly warm motor. And during the caucus, as Mr. Boisjoly have mentioned, something that I'm not usually accustomed to doing, and sitting down between two managers and trying one more time to explain and make sure that I got my thoughts across to them. And after not completing that conversation, but concluding that I probably wasn't communicating, and that may be my fault. I'm happy, or not happy, but readily admit that it may have been my type of explanation. I wasn't getting through. I think that, we had just one last point. I think that we had seen erosion on SRM-15. Erosion, but more important, we had seen blow-through. And it was fairly severe. We had blow-through on 2 field joints, and in fact 2 nozzle joints also. We saw soot between the O-rings in 4 places, as I recall, and that was 53 degrees, and it was my judgment we had no reason to take the risk of shooting at a O-ring temperature that was lower than the 53 degrees. And my recommendation in some of the former meetings was just merely to wait a day. Wait at least until the afternoon, and then depending on temperatures, perhaps waiting another day. And I think that concludes my...
Can you remember any time in your experience in FACOL when the engineering group has been overruled in effect by management?
Nothing that comes immediately to my mind, sir.
Thank you.
The activity report of October 4, 85, to whom was that directed?
I turned that into my immediate supervision for incorporation to go up through the ladder as it reports on a weekly basis.
Who did you give it to? What individual?
My supervisor is Jack Capp. I turned it into his secretary.
Were you given an opportunity to discuss it at any subsequent time with anybody in management?
No, sir.
Thank you.
Just to be perfectly clear about this, is it fair to say that as engineers you don't believe that you had data or analysis to characterize the performance of the joint at a 30-degree temperature?
That's correct.
True with you, Mr. Thompson?
Yes, sir.
Okay, thank you very much.
Thank you.
Now we'd ask Mr. Lund, Mr. Kilminster, and Brian Russell. Eugene Covert is getting in sort of late.
He's on plan B. No, be right.
That's right.
Before you sit down, raise your right hand. You swear the testimony you'll give before this commission may be the truth, all truth, and nothing but the truth? I do.
Mr. Lund, do you want to proceed and make any remarks or give any testimony that you'd care to, and particularly in light of the testimony we've had this morning and this afternoon?
I'm not sure there's anything. We've been over so many things. If there are additional questions, I'd certainly be able to talk about that.
All right. What I'll I try.
Okay.
How do you explain the fact that you seemed to change your mind when you changed your hat?
I guess we've got to go back a little further in the conversations than that. We've dealt with Marshall for a long time, and I've always been in the position of defending our position to make sure that we were ready to fly. And I guess I didn't realize until after that meeting and after several days that we had absolutely changed in a position from what we had been before. But that evening, it was, I guess I had never had those kinds of things come from the people at Marshall, that we had to prove to them that we weren't ready.
I want to move your mic a little bit closer, please.
Okay. And so we got ourselves in the thought process that we were trying to find some way to prove to them that it wouldn't work, and we were unable to do that. We couldn't prove absolutely that motor wouldn't work.
In other words, you honestly believe that you had a duty to prove that it would not work?
That's kind of the mode we got ourselves into that evening. It seems like we've always been in the opposite mode. I should have detected that, but I did not. But the roles kind of switched. So after listening to the verbal presentation in the afternoon, they asked what Thiokol's position was, and I looked around the room, and I was a senior person, and I said, I don't want to fly. Looks to me like the story says that 53 degrees is about it. And of course, we were requested then to go back and do something more and prepare detailed charts and to show that in more detail. So we got busy then, and I gave assignments to a dozen or so people to go out and generate data that would, in a workmanlike manner, show the rationale, show the data that we had, so that everyone would understand all the data and where it came from. And we spent the next couple of hours beating the bushes trying to put together that data. So we did that and began transmitting charts even late then, and then went through that rationale. And all this time, we were preparing the data. The data was coming in. I was trying to put together what I was concluding out of all this, because there was some additional data that was being generated. And trying to understand and to absorb all of the data that was there to, again, see what my thought processes were. And so we stood at the whiteboard there in the Management Information Center, and as the data would come in, we would try and say, now what does this tell us, what does this tell us, and put together a rationale for what we wanted to do. So it was in a real-time mode, and we were trying to absorb the data and put together the story. Well, as a result of that telecon, I gave the charts that made the recommendation that we wait until the motor got to 53 degrees. I didn't see anything different that I hadn't seen before. And, of course, you've heard the story of what happened after that. Now,
let me ask a question.
Yes.
53 degrees. You've stated that it's been often stated that the recommendation was at this point in time to stay within your experience base. But I find that to be a peculiar recommendation in the operation of any kind of system, because normally you say, from our experience base, our data points, our analysis, and our extrapolation, we would be willing at any time to go beyond our experience point out to this far as a next step. And the only reason you would say I'd stay within my experience base is that you had a problem at that point that said you dare not go any farther. So could you clarify in my mind why you said that?
It wasn't a question of that. It was the very definite question of conservatism. You know, this program has people on it, and so I'm very concerned about that. And I want to make sure that if there's any hint of a problem, that we're not extending that. We didn't have any data at that point that would indicate that we should go beyond that. Now, is that an answer to the question, or do you want me to try again?
Maybe a slightly different way of asking that is normally when you're trying to extrapolate beyond maybe beyond your flight experience, you rely on your qualification testing program, and a system or a subsystem is qualified to fly within a certain regime or a certain envelope that would include environmental effects like temperature. Did you have any sort of qualification range on the temperature of the SRM?
Well, yeah, we had development qual motors that were down in the 40s, as has been pointed out. The data, because of the horizontal assembly problems, what we were trying to do is put them back to a condition that would resemble that we would have in a vertical installation. And so we'd gone in and repaired the putty, because when you put those together horizontally, you can't do it the same way. You can't do it the same way. So although the intent was to put them back to the vertical, there's some doubt that you can really do that adequately. And so there's always the question, well, was it perfect? And the answer was it was not. And so my belief is that those 40-degree motors are probably valid and adequate, but there's the doubt.
So going down below, say, 47 degrees or 40 degrees, would be you could consider it
an extrapolation,
perhaps taking it below what the motor had been qualified to.
I think one thing that we need to make very clear is we've talked about SRM-15 and SRM-22 being the two motors that were the blow-by motors, and that we couldn't tell because of those, but we've got to keep in mind there were 10 motors between those, 30 joints between those two temperatures that had no blow-by at all. So I think that as Marshall pointed out, I think Mr. Malloy pointed out, he said, you know, the data is just not conclusive at all, and it wasn't, because we had a low-temperature motor and a high-temperature motor, and we had 10 motors in between that showed nothing.
Could I ask a question on that? In looking at the earlier data, it appears there is erosion and blow-by occurring more frequently later than sooner. And Mr. Boisjoly pointed out that during the year 1985, because of what he learned in looking at inspecting the one motor that he looked at, he developed greater concern. And in line with Neil's question, did you want to stay with 53 rather than, say, exploring something slightly beyond that because there was a greater concern developing? And was his concern
Did you share Mr. Boisjoly's concern? Just why did you stay with 53 again and not say explore a little further?
Well, again, the conservative aspect of looking at what our experience has been, and that was the rationale that we presented to Marshall, is stay within the experience band.
But
don't extend it.
How did you view, you mentioned 10 motors without blow-by, and looking at the data that was handed out this morning, there's several cases of problems with various parts of the motors, and it seemed to be more of it later than earlier.
We haven't been able to identify those parameters that are causing that more pronounced effect.
But if you look at that since you had a problem that was developing to a greater extent, and it was an unknown reason as to why this problem would happen, I can't understand why there wasn't a greater area of concern developing.
Well, there was, and that's why we initiated all of this. What are we going to do with the joint? How are we going to investigate it? Set up a special task team. I took one of my best supervisors, gave him the task of doing that. We assigned Mr. Boisjoly to the task team. We put one of our best project engineers on it. And program manager was assigned, and we implemented a full-time activity to evaluate and do that.
Well, and one more question. Since your people were responsible for the design, were responsible for the testing, were responsible for the qualification, when it came up to the point where there was a question of whether a launch should be made, shouldn't you alone or your organization alone be the one that says yes or not? And why would there be a question coming from NASA because of not having data as well presented as they wanted? Why would they raise questions on your data? And why would you respond to that question? Why didn't you just tell them it's our decision and this is it, and not respond to the pressure?
As a quarterback on Monday morning, that's probably what I should have done. But, you know, you work with people and you develop some confidence, and I have some great confidence in those people at NASA we've worked with. We worked with them for a long, long time.
In what I think I've heard is that your experts were developing a greater and greater concern, including writing rather powerfully stated memos, and it's hard to understand why they didn't get more attention.
I'd like to
in response to your earlier answer about the 10 motors between the 53 degrees and the 75 degrees. One conclusion might be from that database is that you shouldn't operate at 75 degrees or 53 degrees, but you ought to stay within the temperature range of those motors which exhibited no erosion or blow-by. Again, I'm going to ask you the same question I asked before. What was conservative about saying 53 instead of a number other than that, which might be higher or might be lower, depending on how you approach the problem? Trying to understand your thought process.
I guess all of the engineering rationale says that cold was probably worse, that warm was probably better in all the physics of the situation as we best understood them. So we felt that, the conservative thing to do would be to stay warmer.
Yeah, but did you like 53 degrees? Did you like the results on the 53-degree flight?
I would rather have a motor that has no erosion, no blow-by, and looks perfect at the end of the motor firing.
Then might not you not have taken the position that 57 would have been a better number, or 62 or some other number?
We have had, motors down in the low 60s, and I guess there's some, just looking at my chart, in the low 60s at least, that were perfect. We had some in the lower 50s that were not anywhere near as bad as the 15. So there's no clear dividing line, at least in the data.
There's a lot of other factors other than the temperature that might be involved. Is that correct?
That's correct. So we don't know what the effect of the temperature was.
Can I ask one more question? I heard these comments that some tests looked pretty good at 75 and others looked okay at 53. But was the qualification testing thorough enough for any proper database to be in hand to really know what the critical variables are, like the thrust of the motor, the tolerances of the metal joints, the tolerances of the O-rings, or the application of the putty, or the application of the seal? Isn't one of your problems the fact that the qualification testing was inadequate?
It seems like the size of the qualification program is inversely proportional to the size of the motor, which is called dollars, and there's no doubt about that. With small tactical motors, it's not unusual to fire many, 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 and the larger the motor, then the smaller the qualification program. And to get a full statistical range of every parameter in that motor, I don't think there's enough money in the National Treasury to do that. So there's a practical limit to which you do.
Go from a qualified motor and make changes and go into another area of further unknown exploration, like reducing the strength of the motor, or increasing the thrust, or changing the putty.
There were qualification motors, of course, to do the strength of or the thickness of the case and the thrust change.
Well, were they adequate?
Engineering opinion, yes.
I have a question on Mr. McDonald testified that he had a discussion, I believe it was with Mr. Malloy,
about the meaning of the temperature range of 40 to 90 degrees, whether it applied just to the bulk temperature of the motor or whether it applied to every part of the shuttle. What's your understanding?
You would have asked me a month ago. I would have told you the motor is 40 to 90.
So there was no qualification in your mind on the O-ring temperature. For example, the O-ring temperature could have been quite cold because the O-ring is certainly going to move in temperature with the metal case. The metal case could be quite a bit colder than the bulk temperature of the propellant if the weather had been cold.
There was no full-scale motors fired below 40.
But what I'm asking is, did you, as the supplier of this system to the government, have a specification on the O-ring temperature? Or could the O-ring temperature have been anything?
I don't believe there is a specification on the O-ring temperature other than the material itself.
And what is that specification?
Well, it's a specification that says the material can withstand these kinds of environments.
But it doesn't specify the operational aspect, does it?
To my knowledge, no.
In fact, the mill spec says specifically that the O-ring should be qualified for whatever uses they're put to. Mm-hmm. So did you take any steps to do that? That is, qualify the range of temperatures over which these O-rings were to be used?
The development motors were fired from 40 to 84, and the qualification motors from 45 to 83.
So then 40 degrees was the temperature limit for the O-ring?
In the full-scale qual program, that's correct.
So when it was predicted that the temperature of the O-ring at launch, 51L, was going to be 29 degrees, the O-ring was outside of the qualification temperatures by some 10 degrees.
That's correct.
Then how could you make a recommendation to launch if you're 10 degrees outside of your qualification?
Our original recommendation, of course, was not to launch.
Well, I understand that, but your final recommendation was to launch.
Okay. What we need to do then is go through that rationale.
So you're going to answer my question then at the end of this discussion, hopefully?
Well, do you want me to go through it now? I'd be glad to do it now.
I mean, I think we've heard what the explanation you've given. I think the problem we're having is that it's not convincing. I mean, let me, if you don't mind, Arthur. I assume you have great confidence in your engineers, Boisjoly and Thompson and the others. And they're probably as well qualified as anybody in the country that's dealing with these problems, O-rings and seals and so forth. Is that right?
Yep.
And You had a long discussion in the telecom, and you decided, all of you, I understand, all of you decided that for safety reasons you would oppose the launch. Thereafter, NASA, in one way or another, made it clear that they were displeased with that recommendation. And I assume that you knew when you made the recommendation that your recommendation, in fact, was going to determine whether that shuttle would be launched or not, because NASA had indicated to you they would not fly unless they had a written report from Thiokol saying you approved the launch.
I didn't know that NASA would accept that.
You didn't know that?
No, I didn't.
Well, you must have known your recommendation was very important. You knew that if you voted against the launch, it would not have been launched, didn't you?
Well, we had voted prior to it, and they didn't accept it, so I couldn't forecast what NASA would.
No, but you knew that that was the reason they asked you to reconsider. That's why you had the 5-minute recess, didn't you?
That's a fair statement, yes.
Now, knowing that, and knowing that the safety of the crew was involved, and knowing your own people, the engineers that you respected, were still against the launch, what was it that occurred in your mind that satisfied you to say, okay, let's take a chance?
Well, I didn't say take a chance because I felt there was some rationale that allowed us to go ahead.
Well, maybe that isn't fair. Then what was it that occurred in your mind that caused you to be willing to change your mind?
I guess one of the big things is that we really didn't know whether temperature was the driver or not. We couldn't tell. We had hot motors that blew by and cold motors that blew by, and some very near either end that did not. The data was inconclusive. So I had trouble justifying in my own mind and saying, by golly, temperature is a factor. Second,
may I interrupt for just one moment? Mr. Boisjoly has said that the thing which was compelling to him was that the blow-by on the coldest motor was much more severe. He's emphasized how black was the blow-by, how large an angle over which it occurred.
But 3 or 4 degrees above that, there was zero.
So his discussion was not convincing to you.
Well, it wasn't totally convincing because, at 2 or 3 degrees, it went from very, very bad to no problem.
Mr. Lund?
No blow-by.
The flights. There were many seals that didn't have any problem.
That's right.
So it's obviously a random effect. It depends upon whether or not you get a blowhole or you don't get a blowhole. So that if in a particular flight it happens that all 6 seals don't get a blowhole, that's no information. The fact that, as far as I can understand this, it doesn't mean you're suddenly good because it worked, and the next time when one goes off, you're suddenly bad.
Well,
it seems to me that it has to be understood as a probabilistic and confusing, complicated situation, that we're never going to be able to decide that they're all going to break or they're all not going to break. It's not the wonderful one-horse shed. And when you look at it that way, then it's a question of increasing and decreasing probabilities that we have to consider rather than did it work or didn't it work. And I'd like you to explain it to me from that point of view.
Well, the question still is temperature the thing that caused the SRM-15
But
effect?
you heard your engineers argue that there was an effect of temperature which looked like it made things worse. Is it not inconceivable that there's something else that sometimes produces blow-by, that there's more than one effect, and that the temperature could still be an important effect and increase the probability in spite of the fact that at a high temperature it gets worse? Is there any evidence that temperature is not an important matter just because at some high temperature you have an accident?
Well, as you point out, there are many variables in the thing, and it wasn't clear that temperature was the effect.
It was logically clear from the point of view of the engineers. They were explaining why the temperature would have an effect. When you don't have any data, you have to use reason.
Okay.
And they were giving reasons.
That's right. And that's what we did, is we included in our rationale the fact that, sure enough, the temperature could be an effect. Okay. It wasn't clear, but we said we will consider that to be so.
I have great difficulty with this. In usual practice, when there's any real doubt about flight safety, whether it's aircraft or whatever, you simply don't. And it seems to me this is the reverse. And I just have great difficulty understanding the question that's been asked before, that is, understanding any answer. I just haven't heard it as to why, if there is doubt in your mind, why you went ahead, why you changed your mind. I just don't understand it. I appreciate very much if you could explain that.
Maybe we ought to go to Kilminster, if you don't mind. He signed the telefax, and we've asked Mr. Lund a lot of questions, and I think maybe in fairness to Mr. Lund, Mr. Kilminster, can you attempt to explain to the Commission why, I guess you changed your mind too, didn't you?
Yes, sir. Based on the discussion that we had and the rationale that was developed.
Now, how can you say you changed your mind when you say temperature data not conclusive on predicting primary O-ring blow-by? Did you have a feeling you had to prove that it was, the burden of proof was on you to show that it wasn't safe?
No, I think we were asked to relook at the data, which we did.
But could you tell me what data was that you looked at that was different from the data you looked at first?
There was one piece of data that we looked at, which has been discussed before. That was the erosion parameter and the factor of 3. But my evaluation was...
Is that the only new piece of data?
That's really the only new piece of data that we had not previously discussed on the telephone. But I think that the data that we did show, the fact that we had subscale tests at 30 degrees showing no blow-by, was an indicator. We, as Mr. Lund pointed out, had other flight motors at temperatures between the two in question, that is 75 degrees and 53 degrees O-ring temperatures, that had shown no blow-by. And we had static test motors at temperatures lower than 53 degrees that had no blow-by. Now, I'd like to discuss that just a moment.
Could you particularly, though, point out the new data? Because the purpose, as we understand it, for the recess was to find out if there was any new data, or were you just asked to change your mind based on the data you had?
All right, the one piece of data that was new in our discussion was that if we did have blow-by past the primary O-ring, as it was being positioned to seal, and recognizing the fact that the cold temperatures could cause that timing function to extend, then we had an opportunity perhaps of having some erosion occur. We looked at the erosion that had occurred on 51 Charlie and compared that to the data that we had developed both from cold hydraulic oil testing and from hot subscale testing that indicated that very flight had a safety factor of 3 over what would have to have happened in order to get to an area of questionable sealing capability. With that information in mind then, and also the fact that we had some analytical work done earlier to develop the limiting erosion parameters on O-rings, led me to believe that we were in a condition of having a safe position for recommending a flight relative to erosion.
Excuse me. How come that data wasn't available the first time? How did it happen to show up at the recess?
Well, it was just a matter of a discussion that we had while we had the recess, when we said that, well, if indeed the temperature is going to cause a longer time for the primary O-ring to function, and there is the possibility of additional erosion, then where do we stand relative to 51C, and how much more margin did that exhibit?
So you really had the data there before you
yes.
You hadn't analyzed it. In other words, it was not new data, just data you hadn't properly analyzed, right?
It was data that we hadn't prepared or discussed on the earlier portion of the telecon.
And that was through an oversight?
Well, I don't know if it was an oversight or just another piece of data that we were searching for in order to establish our position.
You're saying that you had a factor of 3 over the 51C erosion problem. How how are you attempting to analyze how the timing function would change and how much erosion that could possibly give you on 51L?
Only on a subjective basis, that if, as has been stated, the timing function under cold condition was to extend, and if what was observed under 51C, not only the blow-by but the erosion were combined, then we developed the rationale about that safety factor of 3.
Kilminster, do you have any feeling of pressure being put on you by NASA, or were you just calmly reassessing?
I felt that the pressure that was put on us was to go back and look at the data, look at the detailed information that had been presented, to see if there was something that we were seeing that we were not representing on the phone.
You didn't feel that they were trying to get you to change your mind?
I did not feel a significant amount of pressure in that regard.
Kilminster, have you had an opportunity to look at the correspondence of Mr. Boisjoly written in the summer and autumn of '85?
No, I have not.
Mr. Boisjoly.
To you, 31 July, rather. You received that and read it, I presume.
Yes, and we took immediate action on that, and we established the O-ring task team within a week or so of that memo.
Did you pass along Mr. Boisjoly's concerns to anyone at NASA?
The normal process of that sort of information is through the project office, and Mr. McDonald and so on were on that. That would be their task.
Well, then you're saying that it would have been Mr. McDonald's responsibility to alert NASA that a key engineer thought a catastrophe was possible.
Well, I think NASA understood that clearly, and we've been working with them since that time on this whole problem.
I'm not asking that. I'm asking whether, as a result of Mr. Boisjoly's memo to you, you or Mr. McDonald or anyone else at Firefall alerted NASA to the concerns of this key engineer.
I did not call anyone at NASA specifically, but I saw that they were alerted because of their immediate response in working with us.
But are you aware of their having heard that a potential catastrophe was possible?
I'm not aware.
I'd like to ask a couple of questions about temperature, if I may, a sequence of questions. You say that on this 40 to 90 degree launch or certification criteria, is this a cold soak or is this some other kind of a temperature?
The 40 to 90 degrees is a mean bulk temperature of the propellant, which means to me that we could have a motor where the propellant grain was soaked out to 40 degrees, or conversely, propellant grain was soaked out to 90 degrees.
What's the time constant on this case plus the insulator and so forth, and to get to a equilibrium bulk temperature?
We ran some calculations based on equilibrium at the Cape, and I believe it's about 30 days.
So that it's possible to be exposed to a cold temperature and have sharp temperature gradients within the propellant or the insulator, and so part of it would be at a temperature far outside of what you think would be appropriate, and the rest of it would still be warmer, shall we say.
Yes, but I think that is limited by the other requirement, which was spelled out in a level 2 document that said 31 degrees to 99 degrees.
Is it possible that some of it could be at 26 degrees and other at 55 degrees? Considering, again, a 21 to 30 day transient to get to the bulk temperature.
That's not the way I would read the combined two specifications or two requirements.
Is it possible that there is a difference between the behavior of the subscale motors at some temperature and the behavior of the large motors at the same temperature if one was in thermal equilibrium and the other was in some sort of a non-uniform temperature distribution?
Yes, I would expect there could be some differences.
So there may be some doubt in your mind about how exactly to apply the subscale motor data within the framework of a large-scale motor if you allow for the temperature transient.
Yes, sir.
All right, thank you.
For Mr. Lund or Mr. Russell, when I was talking with you a few days ago at your plant, I think I'm correct in recalling that one of you told me that if the temperature at the Cape on the day of launch had been in the 9 to 10 degrees above zero Fahrenheit range, there would be no question but that you would have stuck to a no-launch position. Am I right in that recollection?
That's right. There's many, many things in the motor then that we'd be concerned about.
So you did recognize that temperature was a discriminator in an absolute sense. The only question was what the margin was, below 53 degrees. Is that correct? Were you acquainted at all with this correspondence, which I assume you had a chance to read, of Mr. Boisjoly, written in the summer and autumn of '85? It seems to say that management does not have an adequately heightened sense of the urgency of the work to be done on the O-ring problem, the seal problem. My question is, were you aware of that feeling on his part at the time? Did it cause you concern, and what, if anything, did you do about it?
I didn't meet with Mr. Boisjoly. I met with Don Kettner, who was the task team leader. He made recommendations to us, and I think we followed those recommendations and did everything we could to help them with them. Now, there undoubtedly are things that were bugging them that they didn't bring to my attention, that I didn't do anything about because I didn't know about them. But when they came, and Don Kettner particularly, we worked very hard with him to try and establish and take corrective action as needed.
Thank you.
I'm sure that all of you and everybody associated with Shuttle knew that it was NASA's intention to fly on a very rapid time schedule throughout the year, or build up to the point of that, and that they would have to launch on winter mornings and other time. In the process of evaluating the information brought to you, did you at any time suggest to NASA that the launch commit criteria, the LCCs, or other rules may be insufficiently constraining, and that you ought to establish rules with respect to the SRM that kept you, either within your experience base, your qual test, or your extrapolations?
We did not. Mr. McDonald evidently had some discussions with him on that line.
Thank you.
Question for Mr. Russell. Perhaps you would give us your recollection of the thought process followed in your mind in the change of position between the view presented in the telecom that Thiokol was opposed to a launch and the subsequent conclusion of the caucus within the company.
I was part of the overall day's efforts that started off pretty early, as has been mentioned, and as the day developed, pretty much agreed with the recommendations. And as our presentation was made on the charts, the subsequent answers that came back, you've asked others if they felt pressure and undue pressure, and I felt some pressure with some of the comments. I thought our rationale was reasonable. I've seen many instances in the past where we have used previous limits for data on putty that I'm familiar with and other raw materials, for example, that we do not exceed our experience base in the usage of these materials, and so I felt that this was the proper thing to do, albeit our 53-degree experience that has been mentioned wasn't desirable, but we had deemed it acceptable at that time. And the statements that seemed to me to put pressure, or at least to make me feel the pressure, were the responses of being appalled at our recommendations, the responses of when we should launch, how long do we have to wait, April, and also there was an argument about what sort of rationale we could have for 53 degrees. And Mr. Armstrong made the point that what temperature could we make a strong statement on, and the data couldn't tell us which temperature other than 53 degrees, which had been our previously most successful low temperature. And so I felt some pressure based on those comments. I'd like to add that my feeling as I believe it was Mr. Malloy, and this is again by voice recognition, but after we had made our recommendation initially, he talked for about 5 minutes and explained in his mind why the data really didn't add up to the conclusions that we had made. And I'll have to admit at that time that it was a very logical presentation that he had made. And then there was talk back and forth as to what the data really meant. And as has been mentioned here, in the caucus, there weren't any new data brought up that I recognized. We pretty much talked over the same types of things, and my feeling of it is what some of us were understanding and what others were understanding and feeling important didn't really agree. I think I can only recall making one comment in the caucus. I can't even remember what that was, and it was very brief, and I don't think made a big impact at all. And the reason that I didn't make so many comments, despite what I felt, was that Roger and Arnie were making the points to the best that they could, and I couldn't see a way of making them any better. So we got to a point in the caucus where Mr. Mason said, and rightfully so, we're covering the same information. We're not talking about anything new here, and it's time for a decision. And I maybe tend in my position to feel pressure more so. I know these other gentlemen have many pressures from all sides, and so I can't really speak for them, but I felt pressure that we were, and I don't know if Roger was referring to me in his testimony, but he could have been, because I had the feeling that we were it was a distinct feeling that we were in the position of having to prove it was unsafe instead of the other way around, which was a totally new experience. And I believe I made that statement afterward. I know I did when I went home and talked about it with my wife. But here again, I think it's impossible for me to say what might have swung the decision, but I felt in my mind that once we had done our very best to explain why we were concerned, and we meaning those in the camp who really felt strongly about the recommendation of 53 degrees, the decision was to be made, and a poll was then taken. And I remember distinctly at the time whether I would have the courage, if asked, and I thought I might be, what I would do and whether I would be alone. I didn't think I'd be alone, but I was wondering if I'd have the courage. I remember that distinctly, to stand up and say no. However, we were not asked as the engineering people. It was a management decision at the vice president's level, and they had heard all that they could hear, and I felt there was nothing more to say, that we could change anything, and also felt in my mind that I didn't see, and I believe I mentioned this to you last week, that I didn't see a dangerous concern. I knew we were entering into increased risk, and I didn't feel comfortable doing that. I was nervous. You asked how I slept that night, and I said I thought I slept okay. My wife differed with that as I talked with her after that, but there was a nervousness there that we were increasing the risk, and I believe all of us knew that if it were increased to the level of an O-ring burn through, what the consequences would be, and I don't think there's any question in anyone's mind about that. I don't know if I've answered the question. I guess your original question was what I thought was in the thought process, but that was what was in my thoughts.
Thank you very much.
Thanks, Bob. I just wanted a question. I think we'd like to adjourn for today. Did either of you gentlemen, Mr. Kilminster or Mr. Lund, have any pressures, outside pressures? Did anybody call you? Anybody suggest you should vote to launch? Anything of that kind at all the Commission should know about? Either one of it?
No, sir.
Okay. Thanks very much. We'll adjourn today.